scientists may have found a faster route to Mars, hidden inside asteroid tracking data. The clue came from asteroid 2001 CA21, whose early orbit pointed to a rare 2031 alignment. That could allow Mars transfers in 56 days, or even an extreme 33 days, but this is not a free shortcut. It trades time for speed, fuel, heat, and brutal braking problems. So the real question is not just how fast we can reach Mars, but whether we can survive arriving there. An asteroid's orbit has a plane. That plane is basically the tilted path the asteroid follows around the Sun. If that plane crosses near Earth's orbital region and also crosses near Mars's orbital region at the right time, scientists can test whether a spacecraft can use a similar path for a fast transfer. That is the core of the discovery. The asteroid in this story is called 2001 CA21. The name is not dramatic, but the result connected to it is. The important detail is not its size. It is not its shape. It is not its composition. It is not whether it is a major threat. The important detail is that an early calculated orbit for this asteroid created a useful Earth-Mars geometry. That early orbit placed its path in a way that crossed the orbital regions of Earth and Mars. That sounds simple, but it is not. In spaceflight, the right geometry can matter as much as the engine. Earth is moving. Mars is moving. A spacecraft cannot just aim at where Mars is today. It has to arrive where Mars will be later. So mission designers look for timing, direction, speed, and alignment. If those variables work together, a route can become much faster. But there is a catch. Early asteroid orbit estimates can change. When astronomers first discover an asteroid, they may only observe it for a short time. That means the first orbit solution can have uncertainty. Later, when more observations are added, the orbit becomes more accurate. The official path may shift. That means the early orbit of 2001 CA21 may not represent the asteroid's final refined path, but that does not make it useless. The early orbit can still be useful as a candidate plane. It can still point to a possible spacecraft trajectory family. In other words, the asteroid does not need to actually travel that exact path forever. The early path can still give mission designers a direction to test. That is why this is not a claim that nature built a permanent highway to Mars. It is a trajectory search method. The study used early asteroid orbital data to look for rapid Mars mission opportunities. It tested Mars opposition years in 2027, 2029, and 2031. Mars opposition is when Earth passes between the Sun and Mars, and the planets are on the same general side of the Sun. These are important periods for Mars mission planning because the geometry is more favourable, but opposition alone is not enough. Mars being closer does not automatically mean Mars is easy to reach. A fast route also depends on the angle of the transfer, the plane of the spacecraft's path, the speed at departure, the speed at arrival, and whether the spacecraft can return. That is where the CA21 derived plane became important. The search looked for paths that stayed close to the asteroid's orbital tilt, within about 5 degrees. That small detail is critical because changing the plane of a spacecraft's orbit costs a lot of velocity, and velocity means fuel, mass, engine performance, and mission risk. So the question became sharper. Is there a future year when Earth, Mars, and the CA21 derived plane line up well enough to create a very fast round trip? The best answer was 2031. That is where the numbers become hard to ignore. The extreme mission profile is 33 days from Earth to Mars, 30 days on the Martian surface, and 90 days back to Earth. Total mission time, about 153 days. That is a shocking number. A normal Mars transfer is usually discussed in terms of many months. This proposed route cuts the outbound leg down to about 1 month. That does not mean a mission is ready. It means the trajectory math found a possible rapid transfer for that alignment. And that distinction is important. Identifying a trajectory opportunity is not the same as approving a mission. A spacecraft still has to launch, survive deep space, hit the target, slow down at Mars, support the crew or payload, return home, and survive Earth re-entry. The path may exist in the math, but the vehicle has to survive the physics. The 33-day version is the extreme case. It is fast, but it demands a lot. The spacecraft would have to leave Earth with very high speed. It would arrive at Mars with very high speed. That makes braking much harder. Mars arrival becomes one of the biggest problems. The mission may save time during cruise, but it creates serious demands for propulsion, heat shields, guidance, and possibly aerocapture. That is why the second mission profile may be more important. The less aggressive version is 56 days from Earth to Mars, 35 days on Mars, and 135 days back. Total mission time, about 226 days. That is still extremely fast compared with standard Mars mission thinking. It is not a small improvement. It is a major reduction in travel time. For a crewed mission, that could matter a lot. Less time in deep space means less time exposed to radiation, less time in microgravity, less time relying on closed life support, less food, water, oxygen, and spare capacity needed for the cruise phase. But even this version must be treated carefully. The word feasible does not mean easy. It does not mean ready with current spacecraft. It means more reasonable compared with the extreme option. It means the route is mathematically coherent and less punishing than the 33-day version. Full mission engineering would still be needed. That is the part that makes this discovery exciting but also dangerous to overstate. The shortcut is not a shorter straight-line distance. Spacecraft do not travel through the solar system the way cars travel between cities. They move around the Sun, while Earth and Mars are also moving around the Sun. A faster Mars transfer usually means using more energy, not less. So the shortcut has a specific meaning. It means a transfer that reaches Mars in much less time by using better timing, better plane alignment, and higher speed. It may reduce travel time, but it may increase departure energy. It may reduce crew exposure to deep space, but it may increase arrival danger. It may make the mission shorter, but not automatically simpler. That is the real trade. Time goes down, energy goes up, braking becomes harder, safety margins may shrink, mission design becomes more intense. And that is why this is not just a story about a single asteroid. It's a story about using asteroid data in a new way. The same data collected to protect Earth may also help identify faster paths through the inner solar system. Near-Earth asteroid catalogues contain many objects with many different orbital planes, timings, and crossings. Each one may act as a possible clue for mission designers. Most of those clues will lead nowhere. Some will be too expensive, some will not line up with Earth and Mars at useful times, some will fail when tested with real planetary positions. But one clue from 2001 CA21 produced specific rapid Mars transfer profiles for 2031. That is enough to make the method serious. The asteroid did not solve Mars travel. It did not give us a finished mission plan. It did not remove the need for powerful propulsion or dangerous braking. But it showed that asteroid orbit data can reveal transfer opportunities that standard thinking might miss. And that changes the question. The question is no longer only how fast we can build better rockets. The question is also how many useful routes are already hidden inside the orbital data we have been collecting for years. Mars looks close in pictures, but the normal trip still takes months because Mars is never waiting for us. That is the first thing most people get wrong. A spacecraft is not launched at Mars as if Mars is a fixed object in the sky. Mars is moving around the Sun at high speed. Earth is moving too. The spacecraft is also moving around the Sun the moment it leaves Earth. So a Mars mission is not a straight shot from one planet to another. It is a timed interception. You are not aiming at where Mars is, you are aiming at where Mars will be. That one fact controls almost everything. The launch date, the direction of departure, the speed, the arrival angle, the fuel demand and the return plan all depend on timing. If the spacecraft leaves too early, Mars will not be there. If it leaves too late, Mars may have already moved away from the best arrival point. If the spacecraft is too slow, it misses the useful window. If it is too fast, it may arrive with so much speed that stopping becomes a major problem. This is why NASA describes Mars flight as hitting a moving target. The spacecraft must be placed onto an interplanetary path that reaches Mars's orbit, at the same time Mars reaches that same region. That sounds simple, but it is one of the hardest parts of deep space travel. And this is also why launch windows matter so much. For a minimum energy Mars mission, Earth and Mars only line up properly about every 25 months. Sometimes people round this to about 26 months. That means you cannot just launch a low-energy Mars mission whenever you feel ready. You wait until the planets give you the right geometry. Rockets are powerful, but they do not erase orbital timing. They still have to work with the motion of the planets. That is the baseline. Mars missions take months because the route is controlled by orbital phase timing and energy, not distance alone. That is the part that makes the CA21 shortcut idea interesting. It is not simply saying go faster. Anyone can say that. The real question is whether there is a specific future alignment where a much faster path is mathematically possible without completely destroying the mission with impossible plane changes and impossible timing. But to understand why 33 days or 56 days sounds so extreme, you first need the standard number. The classroom Mars route is usually based on something called a Hohmann transfer. The name sounds technical, but the idea is straightforward. It is one of the most energy-efficient ways to move between two circular or near-circular orbits around the Sun. You leave Earth's orbit, follow a stretched path around the Sun, and meet Mars near the far side of that path. This route is popular because it saves fuel, but it does not save time. Earth orbits the Sun at about 1 astronomical unit. Astronomical unit means astronomical unit, which is the average distance from Earth to the Sun. Mars orbits farther out, at about 1.52 astronomical units. A Hohmann-style transfer between them uses an orbit with an average size of about 1.26 astronomical units. When you use Kepler's third law, which connects orbit size with orbit time, the full transfer orbit takes about 517 days to go around the Sun. But a Mars transfer only uses half of that stretched orbit. So the Earth to Mars leg comes out to about 259 days. That is the famous comparison point. About 259 days for a classic low-energy one-way cruise. Around 8.5 months. That is why Mars travel is usually described as a 6 to 9 month journey. The exact number changes with the mission, the launch window, the spacecraft, and the chosen trajectory, but the basic scale is months, not weeks. Now place that next to the CA21 derived numbers. A standard Hohmann-style cruise, about 259 days. The proposed CA21 derived feasible outbound leg 56 days. The extreme outbound leg 33 days. That is not a small improvement. That is not shaving off a few weeks. That is a completely different class of Mars transfer. It takes the idea of a months-long cruise and compresses it into a time span closer to a long expedition on Earth. But there is a reason we do not normally do that. Low-energy routes are slow because they use the Sun's gravity efficiently. They do not fight the orbital system too hard. They let the spacecraft coast along a path that does not demand extreme speed. That makes them attractive because propellant is one of the biggest limits in spaceflight. Propellant is not just fuel sitting in a tank. Propellant is mass. Mass decides the size of the rocket. Mass decides how much payload you can carry. Mass decides whether the mission can launch at all. If you need more propellant, the spacecraft becomes heavier. If the spacecraft becomes heavier, you need even more propellant to move it. That is the trap every mission designer has to fight. So when NASA and mission planners prefer low-energy transfers, they are not being slow for no reason. They are protecting the mission from the rocket equation. They are trying to send the spacecraft with a realistic launch vehicle, realistic fuel mass, realistic arrival speed, and realistic safety margin. That is the trade. The classic path saves propellant. The shortcut saves time. But time is not the only cost. A faster trajectory means the spacecraft must usually leave Earth with more speed. That can require a more powerful launch system, in-space refueling, advanced propulsion, or a smaller payload. Then the spacecraft reaches Mars faster, but it also reaches Mars with more energy. And that energy has to go somewhere. It has to be removed. That means braking. A Mars orbiter may need a large engine burn to enter orbit. A lander may need to survive intense atmospheric entry. A crewed ship may need a very controlled capture sequence. The faster the arrival, the harder this becomes, so a fast route can reduce cruise time while increasing arrival danger. This is why faster does not automatically mean better. A 33-day Mars trip sounds amazing. For crew health, it could reduce radiation exposure and time in microgravity. For mission psychology, it could make the journey feel less like a long isolation event. For life support, it could reduce consumables, but it also forces the spacecraft into a much harsher energy regime. The launch is harder, the arrival is harder, the return may be harder, the safety planning is harder. So the real question is not, can Mars be reached faster? The real question is, can Mars be reached faster with a spacecraft that can actually launch, brake, survive, and return? That is where launch windows become even more important. Mars missions have always been shaped by windows. A useful Mars launch opportunity comes roughly every 26 months, because Earth catches up to Mars in a repeating cycle. Miss that window, and the mission may have to wait more than 2 years. That affects everything. Rocket readiness, spacecraft testing, crew training, cargo staging, surface mission planning, return timing, emergency options. A Mars mission is not one flight. It is a chain of timed events. The outbound flight has to work, the Mars arrival has to work, the surface stay has to match the return geometry. The return vehicle has to leave Mars at the right time. The Earth arrival has to be survivable. Every part is connected to the motion of the planets. That is why a shortcut would matter if it is real and usable. It would not just reduce the number of days in space, it could change the entire architecture. A shorter round trip could reduce the need for a very long surface stay. It could change how much food and water must be carried. It could change radiation shielding requirements. It could change the way cargo is sent ahead. It could change how mission planners think about abort options and rescue timelines, but only if the energy price can be paid. This is the tension at the center of the whole story. The ordinary Mars route takes months because it is built around energy efficiency and planetary timing. The CA-21 derived route challenges that baseline by asking whether a rare geometry in 2031 could support a much faster transfer. That does not mean the 33-day version is ready. It does not mean a crew can launch on it. It does not mean NASA has approved it. It means a trajectory opportunity was identified in the model. That phrase matters. Identified as a trajectory opportunity is not the same as approved mission design. A trajectory opportunity means the math can connect Earth and Mars in that time under the chosen assumptions. An approved mission design means the spacecraft can be built, launched, navigated, protected, slowed down, landed or captured, supported, and brought home with acceptable risk. Those are very different claims. So when you hear 259 days versus 56 days versus 33 days, do not hear it as a simple race. Hear it as a change in the mission problem. The 259-day route is slow, but it is energy efficient. The 56-day route is fast, but still presented as the more serious rapid option. The 33-day route is extreme, dramatic, and brutally demanding. That is why this discovery matters. It does not erase the old physics. It exposes a possible way to trade one problem for another. Instead of accepting a long cruise, the mission accepts higher speed. Instead of saving fuel, it saves time. Instead of a gentle arrival, it may face a violent braking challenge. And that is where the story becomes more intense. Because if Mars normally takes months because the planets are moving targets, then the asteroid clue matters for one reason. It may reveal moments when those moving targets briefly line up with a faster path. The old baseline says, Mars is hard because timing controls everything. The new question is whether asteroid data can uncover better timing than we knew how to search for before. The strange part is this. The asteroid does not have to be useful as a destination to be useful as data. That is the key shift. Most people hear asteroid and think about mining, impact threats, or maybe a spacecraft landing on a small rock. But in this Mars shortcut story, the asteroid is not important because we want to visit it. It is important because its orbit contains information. Near-Earth asteroids are natural objects moving through the solar system without engines. They are not choosing their paths, they are being shaped by gravity, by repeated planetary pulls, by small changes over long periods of time, and by the structure of the solar system itself. That makes them useful in a very specific way. They show us how objects can naturally move. A spacecraft has engines, an asteroid does not, but both must obey the same gravity. So when scientists track asteroids, they are not only tracking rocks, they are recording real examples of motion through space. Those paths can pass near Earth, near Mars, near Venus, or through parts of the asteroid belt. Some paths are dangerous, some are harmless, some may also be useful clues. That is why asteroid databases matter. NASA's near-Earth object tracking work is built for planetary defense. The goal is to calculate where these objects are going and whether any of them could become a future threat. But the same orbit catalogues can also be searched in another way. Instead of only asking, could this asteroid come near Earth? Mission designers can ask, does this asteroid's path reveal a useful route shape? That is a different question, and it is the reason small body orbits matter here. Asteroids are like test cases created by nature. They move through the same gravitational system that spacecraft must move through. They cross regions, they repeat patterns, they enter resonances, they get pushed and pulled by planets over time. Their orbits can show which parts of the solar system are dynamically connected. That does not mean every asteroid orbit is useful for a mission. Most will not be. Many will point to paths that are too slow, too steep, too energetic, or badly timed. But if you have thousands of asteroid solutions, you can start searching for rare cases where the geometry is interesting. And 2001 CA21 became one of those cases. The important part is that the CA21 clue came from early orbital data. That sounds risky because early orbit estimates can be uncertain. When an asteroid is first discovered, astronomers may only observe it for a short time. They may have a short observation arc, meaning they have only seen a small piece of the asteroid's motion. From that small piece, they calculate an orbit. But the first answer may not be final. Later, as more observations come in, the orbit gets refined. The uncertainty shrinks. The official path becomes more accurate. Normally, the early uncertain version is something scientists want to improve or replace, but this story turns that idea around. The early orbit does not have to be the asteroid's final true path to be useful for trajectory design. It can still contain a geometry worth testing. It can still suggest a plane, a tilt, and a crossing pattern. Even if the refined asteroid orbit changes later, the early solution can act as a candidate shape for spacecraft trajectory searches. That is why this discovery feels unusual. Preliminary data, the kind of data that is usually treated as incomplete, became the starting point for a rapid Mars trajectory search. The early CA21 orbit may not be the final story of the asteroid itself, but it still pointed toward a possible Earth-Mars transfer geometry. That distinction matters. The study is not saying the asteroid will drag us to Mars. It is not saying the asteroid has a strong enough gravitational field to help a spacecraft. It is not saying astronauts should dock with CA21. Most asteroids are far too small to provide a meaningful gravity assist. Their gravity is extremely weak compared with planets. The useful part is not the asteroid's gravity. The useful part is the asteroid's orbital plane. Every orbit around the Sun has a plane. Some are almost aligned with Earth's orbit, some are tilted. The CA21 derived idea focused on a plane that could connect regions near Earth and Mars at the right time. The search looked for spacecraft paths that stayed close to that asteroid-related tilt, within about 5 degrees. That number matters because small angular differences can become expensive in space. If a spacecraft is already moving along a useful plane, it does not need to spend as much energy changing direction. But if it has to leave Earth on one plane, and then force itself onto a very different plane, it needs extra velocity. That extra velocity is called delta V, and delta V is one of the most important numbers in mission design. Delta V is not just speed, it is the amount of velocity change a spacecraft must produce. Every major burn costs delta V. Leaving Earth costs delta V. Correcting the path costs delta V. braking at Mars costs delta V. Changing the tilt of an orbit also costs delta V. And plane changes can be brutal. The faster a spacecraft is moving, the more expensive it can be to rotate its path. That is why mission designers care so much about orbital planes and nodes. A node is a place where one orbital plane crosses another. If a spacecraft can change paths near the right node, or if the planets already line up near a useful plane, the mission may avoid wasting huge amounts of energy just to fix its angle. So the CA-21 approach is not just about going fast. It is about avoiding unnecessary sideways correction. That is the part that makes the method real astrodynamics. The route is not interesting because it sounds dramatic. It is interesting because it tries to find a moment when Earth, Mars, and the transfer plane already cooperate. In that situation, alignment can become as important as engine power, and that is exactly why 2031 appears in the story. The study tested multiple future Mars opposition periods, including 2027, 2029 and 2031. The result was not that every Mars opposition worked. The result was that 2031 matched the CA-21 derived plane more favourably. That means the planet's positions in the candidate plane produced a better fast transfer opportunity in that year. This is a major point. Mars being close is not enough. A close Mars can still be hard to reach if the angles are bad. A slightly less obvious window can become valuable if the transfer plane, relative speeds and timing are better. Spaceflight is not only about distance. It is about geometry and velocity at the same time. That is why the asteroid clue matters. It gives mission designers a way to filter the search. Instead of testing random fast paths blindly, they can use asteroid-derived planes as candidates. Each asteroid orbit becomes a possible starting point for a trajectory search. Most will fail. Some may reveal special windows, that is the bigger scientific lesson. Asteroid catalogues are not just warning lists, they are large data sets of real orbital motion. They show how small bodies move under the combined influence of the Sun and planets. If those catalogues are searched carefully, they may expose useful transfer families that standard planning does not immediately highlight. That is not hype, that is data mining. The same information used to ask whether an asteroid could threaten Earth can also be used to ask whether its path suggests a useful spacecraft route. This does not replace normal mission design. It adds another search method. It gives engineers more candidates to test with real planet positions, real timing, and real energy requirements. And that is where the tension grows. If one early asteroid orbit can produce a 2031 rapid Mars opportunity, then how many other possibilities are sitting inside near-Earth object databases right now? How many paths have been calculated for defense but never searched as mission design clues? How many fast or efficient transfer windows are hidden inside data we already have? This does not mean there are easy routes everywhere. It means the search space is bigger than the textbook examples. Hohmann transfers are not the only options. Standard launch windows are not the only patterns worth checking. Asteroid-derived trajectory searches may reveal rare alignments that normal planning would miss. But the method still has to face the same hard filter every mission faces. A path can look useful in geometry and still fail in energy. It can connect Earth and Mars and still demand too much velocity. It can reduce travel time and still create an arrival problem that is too dangerous. It can be mathematically valid and still not be mission ready. That is why the CA-21 clue is powerful but not a solution by itself. It identifies a possible path family. It does not build the rocket. It does not solve the braking. It does not protect the crew. It does not prove that a 33-day mission is ready. But it changes the starting point of the search. Instead of only asking how to push harder, it asks where the solar system already allows better alignment. And once that question is on the table, the next problem becomes unavoidable. Finding the plane is only the beginning. To prove a spacecraft can actually use it, scientists need the math engine that connects two moving planets across a fixed flight time. That engine is Lambert's problem. The Mars shortcut only becomes serious when the math can connect two moving planets on a real timeline. That is where Lambert's problem enters the story. The name sounds abstract, but the question is very direct. If Earth is at one place in space, Mars is at another place in space, and you choose a flight time, what path connects them? That is the mission designer's problem. Not where is Mars, not how far away is it. The real question is, where is Earth at departure? Where is Mars at arrival? And what orbit can take a spacecraft from one to the other in that exact number of days? This is why Lambert's problem is so important in interplanetary flight. It takes two positions and a time limit. Then it tells you the kind of orbit needed to connect them. If the time is long, the orbit can be gentler. If the time is short, the orbit becomes more aggressive. The spacecraft does not get to ignore gravity. It must follow a path around the Sun, and that path must match the chosen arrival time. This is also why the CA-21 study is not just a vague claim that someone found a shortcut. It is described as Lambert-based. That means the work tested whether Earth and Mars could actually be connected over short flight times, while staying close to the asteroid-derived plane and using real planetary positions. That matters, because without this kind of calculation, 33 days to Mars is just a headline. With this kind of calculation, it becomes a specific trajectory claim that can be tested, challenged, improved, or rejected. And the first hard truth is this: a 259-day Mars transfer and a 33-day Mars transfer are not the same path with a faster engine. They are different orbits. That is where many people misunderstand fast space travel. You cannot just take the normal Mars route and press fast forward. A spacecraft on a 259-day transfer follows a lower energy path around the Sun. A spacecraft on a 33-day transfer must take a much higher energy path. It must leave Earth much faster, cross into planetary space much more aggressively, and arrive at Mars with much more speed. So the shortcut is not free. It buys time with energy. That trade controls everything. If you demand a shorter time of flight, the math responds by increasing the required speed. More speed at departure means more launch energy. More speed at arrival means a harder Mars capture problem. The spacecraft has to slow down somehow, either with engines, atmosphere, or a combination of both. And the faster it arrives, the more dangerous that braking phase becomes. This is why the 33-day number is both exciting and brutal. The geometry may be valid, but the energy demand is severe. That is not a small detail. It is the difference between a beautiful trajectory on paper and a spacecraft that can actually survive the mission. And this is why the 56-day profile matters so much. It is still fast, still far faster than the normal months-long cruise, but it is less extreme. It gives the spacecraft more time to reach Mars, which usually reduces the energy pressure compared with the 33-day case. It does not make the mission easy. It only makes the problem less punishing. But Lambert's problem alone is not enough. A simple diagram of Earth and Mars can trick you. In diagrams, the planets often look like they move in clean circles on a flat sheet. Real space is not that neat. Earth's orbit is not a perfect circle. Mars's orbit is more stretched than Earth's. Their orbital planes are not exactly the same. Their speeds change as they move around the Sun. Their positions on a given date must be calculated precisely. That is why ephemerides matter. An ephemeris is a detailed record or prediction of where a planet or spacecraft is at a specific time. For real mission design, you do not use a cartoon orbit. You use precise planetary positions and velocities for actual dates. The CA-21 work says the trajectories were checked with full ephemeris computation using JPL horizon-style data. That means the study was not only using simple classroom circles, it was testing the paths against real predicted planetary motion. That is important because this shortcut is not a general route that works whenever we want. It is tied to a specific future alignment. That alignment is 2031. And 2031 was not supposed to be magic from the start. The study examined future Mars opposition opportunities including 2027, 2029 and 2031. The method filtered the candidate years. It tested the geometry, it checked which year matched the CA-21 derived orbital plane most favourably. The answer was 2031. That is a very different claim from saying Mars is easiest in 2031. It is more specific. It says that when this asteroid-derived plane was used as a search clue, the 2031 Earth-Mars geometry produced the strongest rapid transfer opportunity among the tested cases. That makes the result more interesting. Because the shortcut did not come from guessing a year and forcing the math to work. It came from searching candidate windows and finding that one of them aligned unusually well. But this also makes the result fragile. If the timing changes, the route changes. If the spacecraft performance changes, the mission changes. If the payload mass changes, the launch demand changes. If Mars arrival requirements change, the whole architecture changes. Fast transfer calculations are sensitive because they depend on the exact positions and velocities of moving planets. That is why real ephemeris validation matters so much. The planets are not symbols. They are moving bodies with exact locations on exact dates. For a fast transfer, small errors can grow quickly, a timing mistake can become a miss, a velocity shortfall can become a failed arrival, a plane mismatch can become a major fuel penalty. This is also why the asteroid plane matters again. The CA-21-derived plane is not just a decoration added after the fact, it is part of the filter. The search looked for rapid paths that stayed close to that plane, because staying close to the plane helps reduce expensive direction changes. That is the connection between the asteroid clue and Lambert's problem. The asteroid gives a candidate plane. Lambert's problem tests whether Earth and Mars can be connected along a useful path in a chosen time. Ephemeris data checks whether the planets are actually in the right places on the real dates. Those three pieces make the discovery stronger than a simple guess, but they still do not make it a mission. That is the line that must stay clear. Lambert arcs can show that a transfer is mathematically possible. They can show that a spacecraft path exists between Earth and Mars for a selected flight time. They can show departure and arrival conditions. They can identify which future window has better geometry. But a complete mission is much harder. A mission needs a launch vehicle that can provide the required departure energy. It needs a spacecraft that can carry enough mass. It needs propulsion margins. It needs navigation correction capability. It needs radiation protection. It needs communication geometry. It needs Mars arrival braking. It needs an orbit insertion or landing plan. It needs abort options. It needs a return strategy. It needs Earth re-entry planning. And if humans are on board, it needs life support, medical safety, shielding, and operational time to handle failures. The math can connect the planets. Engineering has to keep the spacecraft alive. That is why this result should be taken seriously, but not treated as a finished mission plan. The Lambert solution is like the first hard gate. If the math cannot connect Earth and Mars in 33 or 56 days, the story ends immediately. But if the math can connect them, then the next gates appear. Can the rocket launch it? Can the spacecraft survive the speed? Can Mars capture it? Can the crew handle the mission tempo? Can the return leg work? Can the whole system stay within real mass and safety limits? This is where the shortcut becomes more intense. The discovery does not remove the hard parts of Mars travel. It moves the fight to a more dangerous level. Instead of asking whether a fast path exists, the next question becomes whether any real spacecraft can pay the price of using it. That is why Lambert's decision's problem is the engine behind the shortcut, but not the final answer. It proves that the route can exist in orbital mechanics. It does not prove that humans can ride it safely, and that leads directly into the most violent part of the whole concept. The 33-day Mars transfer. It is the number that made the headline explode. It is also the number that creates the biggest engineering nightmare. The fastest version of this route is also the version that creates the biggest problems. The number is 33 days. That is the extreme outbound trip proposed in the CAA-21-derived trajectory study. Earth to Mars in 33 days. Then 30 days on the Martian surface, then 90 days back to Earth. Total mission duration, about 153 days. For Mars, that is not just fast. That is a completely different class of mission. A normal Hohmann-style transfer takes about 259 days one way. That is the slow, energy-efficient baseline. It is the reason Mars trips are usually discussed as journeys of many months. The 33-day profile takes that familiar cruise and compresses it into about 1 month. That is why the number grabs attention, but the same number also creates the danger. Because a spacecraft does not reach Mars in 33 days by taking a normal route and simply moving a little faster. It needs a much more energetic path. It must leave Earth at very high speed, cross interplanetary space aggressively, and arrive at Mars with a huge amount of kinetic energy. That is why this case is called extreme. The route can be geometrically valid and still be brutally hard to fly. That phrase matters. Geometrically valid, but energetically punishing. The math can connect Earth and Mars in 33 days under the right alignment, but the spacecraft has to survive the consequences of that connection. And the biggest consequence is arrival velocity. Getting to Mars quickly is not the end of the mission. It is only the beginning of the next problem. Once the spacecraft reaches Mars, it has to slow down. If it cannot slow down, it does not enter orbit. It does not land. It just flies past Mars at high speed, and the mission fails. Even a normal Mars mission has to deal with this. A slower spacecraft still needs Mars orbit insertion, atmospheric braking, parachutes, retrograde burns, or some combination of systems to reduce speed. Mars capture is never easy. Landing on Mars is never easy, but a 33-day transfer makes that problem much worse. The spacecraft reaches Mars with far more energy. More energy means more speed that must be removed. That can demand more propellant, stronger engines, bigger tanks, better heat shields, more accurate guidance, and tighter margins. Every part of arrival becomes more severe. This is the hidden cost of the shortcut. The cruise gets shorter, but the braking problem gets larger. And for Mars, braking is already one of the hardest parts. Mars has an atmosphere, but it is thin. It is thick enough to heat a spacecraft violently during entry, but not thick enough to make landing simple. That is why Mars is so difficult. The atmosphere helps slow you down, but it does not help enough. You still need heat shields, parachutes, engines, timing, guidance, and a vehicle that can survive the whole sequence. Now increase the arrival speed, the heat load rises, the guidance problem becomes sharper. The time to make corrections shrinks, the spacecraft may face stronger forces, the thermal protection system has less room for error. A small targeting mistake can become a mission-ending problem. That is why aerocapture enters the discussion. Aerocapture means using a planet's atmosphere to slow a spacecraft enough to enter orbit, instead of using engines to do all the braking. In principle, this is attractive because it can save a massive amount of propellant. Mars has an atmosphere, so it is a possible candidate for aerocapture. But aerocapture is not simple. The spacecraft must hit the atmosphere at the right angle, too shallow, and it may skip away and fail to capture. Too steep and it may experience dangerous heating and loads. The vehicle has to survive the thermal environment, control its path, and exit the atmosphere in the right orbit. For a high-speed Mars arrival, aerocapture becomes more tempting and more dangerous at the same time. It is tempting because carrying all the propellant needed to brake from such a fast arrival may be extremely difficult. Using the atmosphere could reduce that propellant burden. But it is dangerous because higher speed means the atmosphere becomes more punishing. Heat shield performance, navigation accuracy, vehicle shape, control authority, and knowledge of Mars' atmospheric density all become critical. And for crewed Mars arrival, this is even more serious. A robotic spacecraft can take risks that a crewed spacecraft cannot. A probe can test the limits. A human vehicle needs far higher confidence. You cannot treat a crewed aerocapture at extreme arrival speed like a simple extension of past robotic missions. The safety requirements are much stricter. So the 33-day route does not just ask for a fast spacecraft. It asks for a complete high-energy mission system. The launch has to be powerful enough. The spacecraft has to handle the departure. The navigation has to be precise. The cruise corrections have to work quickly. The Mars arrival system has to remove a huge amount of velocity. The crew or payload has to survive the entire process. Then, after only 30 days on Mars, the return leg has to begin. That short surface stay is another sign that this mission profile is extreme. A 30-day Mars surface stay sounds useful at first. It is enough time to conduct operations, collect samples, test systems, and prove that humans can work on Mars, but it is also a very compressed schedule. There is little room for delays, little room for equipment failures, little room for medical issues, little room for weather problems, little room for slow recovery after landing. A long Mars mission has its own risks, but it gives time for surface operations. A 30-day stay creates a different kind of pressure. The crew lands, checks systems, performs mission tasks, prepares for departure, and launches again in a narrow timeline. That is not automatically safer, it is simply shorter. And that is one of the biggest misconceptions about rapid Mars travel. Shorter does not always mean safer. A 33-day outbound trip could reduce radiation exposure during transit. That is a major advantage. Deep space radiation is a serious problem for crewed Mars missions. Less time between planets means less time exposed to galactic cosmic rays and solar particle events. It also means less time in microgravity, which reduces muscle loss, bone loss, cardiovascular changes, and other health problems. Those benefits are real. But the mission also becomes faster in the operational sense. The crew has less time to check every system after launch, less time to diagnose slow developing problems, less time to recover from launch stress, less time to perform contingency trajectory corrections, less time to handle medical stabilization, less time to adapt to the spacecraft environment before Mars arrival. A normal long cruise is risky because it keeps people in deep space for months. A very short cruise is risky because it compresses everything. The spacecraft leaves Earth, and almost immediately the mission is moving toward a high-speed Mars arrival. There is less time to discover that a system is underperforming, less time to repair a problem, less time to build confidence before the hardest phase begins. The schedule becomes aggressive from the first day. That is the trade. The 33-day transfer reduces chronic risk, but may increase acute risk. Chronic risk means the danger that grows over time: radiation dose, microgravity damage, isolation, life support wear, consumables use. Acute risk means the danger concentrated into specific events: high-energy launch, fast cruise correction, violent Mars arrival, aerocapture, landing, ascent, return, Earth re-entry. The extreme route attacks the long-duration problem, but it makes the high-energy events more severe. That is why the 33-day number should not be treated as a near-term mission plan. It is a signal. It shows that the geometry may allow an extremely fast connection between Earth and Mars in 2031. It proves that the search method can produce a dramatic result. But it also exposes how far the engineering may have to go. The spacecraft may need propulsion beyond current practical Mars mission capability. It may need advanced thermal protection. It may need aerocapture methods that have never been used for crewed Mars arrival. It may need large margins for navigation and control. It may need a mission architecture designed from the start around high-speed arrival and rapid return. That is not a small upgrade. That is a different way to design Mars travel. And this is why the 33-day transfer is both the most exciting and the least forgiving part of the story. It is the number that makes the discovery feel revolutionary. It is also the number that makes the engineering look brutal. A 33-day Mars trip would change how people think about distance in the solar system. It would make Mars feel operationally closer. It would reduce the psychological weight of a months-long cruise. It could lower radiation and microgravity exposure in a way that matters for human health. But none of that helps if the vehicle cannot slow down. None of that helps if the heat shield cannot survive. None of that helps if the propulsion system cannot deliver. None of that helps if the crew arrives too fast for a safe capture or landing. So the real question is not whether 33 days sounds impressive. It does. The real question is whether the complete mission can survive the speed that makes 33 days possible. That is why the extreme profile should be viewed as the spark of the story, not the most realistic path forward. It shows the upper edge of what the geometry can suggest. It shows how dramatic the CA21 derived alignment could be. It shows why asteroid-based trajectory mining deserves attention. But the serious engineering discussion may not begin with the 33-day version. It may begin with the 56-day version. Because 56 days is still fast enough to change Mars mission planning, but not as violently extreme as 33 days. It may be the point where the shortcut starts to move from shocking headline to serious candidate. The 33-day route gets attention, but the 56-day route may be the one that matters more. That sounds less dramatic at first. 56 days does not hit as hard as 33. But in mission design, the most extreme number is not always the most useful number. The better question is not which route is fastest. The better question is, which fast route has a better chance of becoming real? The second sum. 21 derived profile gives 56 days from Earth to Mars, 35 days on the surface and 135 days back to Earth. Total mission duration, about 226 days. That is still incredibly short for a Mars mission. A normal Hohmann-style Earth-to-Mars transfer is about 259 days one way. The 56-day profile cuts the outbound cruise down by more than 3/4. It does not reduce a Mars trip by a small amount. It changes the whole scale of the mission. And that is why this version deserves serious attention. The 33-day version is the extreme case. It pushes the idea to the edge. It shows that the geometry may allow a very fast connection. But it also creates enormous propulsion and arrival problems. The 56-day version gives the spacecraft more time. That usually means lower energy demand than the 33-day case, lower arrival speed, and more room for real engineering. Not easy, just less brutal. That difference matters. A mission does not become possible because the math is exciting. It becomes possible when the math, the vehicle, the propulsion, the mass, the heat shield, the guidance system, and the crew safety plan can all survive the same design. The 56-day profile is important because it may sit closer to that serious design space. But the word feasible needs to be handled carefully. Feasible does not mean ready to launch. It does not mean NASA has approved it. It does not mean current spacecraft can already fly it. In trajectory research, feasible often means the path works dynamically under the study's assumptions. It means the spacecraft can be mathematically connected from Earth to Mars and back within the chosen timeline and geometry. It means the route is more plausible than the extreme option. That is not the same as mission ready. A feasible trajectory can still demand technology we do not currently have at the required scale. It can still require advanced propulsion. It can still require high-speed Mars capture. It can still require major thermal protection. It can still create a difficult return problem. So the 56-day route should not be treated like a finished flight plan. It should be treated as the more serious candidate. And here is why. For humans, travel time is not just a schedule issue. It is a health issue. A crew travelling to Mars is exposed to deep space radiation. They are outside Earth's magnetic field. They face galactic cosmic rays and the risk of solar particle events. They also live in microgravity, where muscles weaken, bones lose density, and the body changes in ways that affect performance. A 259-day cruise means the crew spends most of a year in that environment before even reaching Mars. A 56-day cruise changes that. It does not remove the risk, it does not make deep space safe, but it cuts the exposure time massively. That could reduce cumulative radiation dose. It could reduce microgravity damage. It could reduce the amount of food, water, oxygen, spare parts, and medical supplies needed during transit. It could reduce the psychological stress of a long cruise. It could make the crew arrive on Mars stronger and more ready to work. That is the practical promise. The point is not only arriving faster. The point is changing the risk equation. A shorter cruise means the spacecraft may not need to operate as a deep space habitat for as long. Life support still has to be extremely reliable, but it has to support the crew during a shorter outbound phase. Consumables planning changes, maintenance planning changes, emergency planning changes, crew training changes, even the mental structure of the mission changes. A months-long crossing becomes a weeks-long crossing. That is a major shift, but the danger does not vanish. It moves. The 56-day route still requires high energy. It still reaches Mars much faster than normal. It still needs serious braking. It still needs a return plan. It still creates a tight surface timeline. 35 days on Mars is not a long expedition. It is a short, intense surface mission. The crew would have to land, recover, check systems, perform priority tasks, prepare for departure, and keep the return architecture on schedule. That is a lot to compress into 5 weeks. So this route does not make Mars simple. It makes Mars different. And the return leg is the part people often underestimate. Many fast Mars concepts focus on getting there. That makes sense because Earth to Mars in 33 days, or Earth to Mars in 56 days is the headline. But a human Mars mission is not a one-way speed test. The crew must come back. The return path can dominate the design because it depends on Mars departure timing, Earth arrival timing, propulsion, life support, and safe re-entry. That is why the CA21 study is more interesting than a one-way stunt. It discusses round-trip architecture. The 56-day profile is not just get to Mars quickly and worry later. It includes 56 days outbound, 35 days on Mars, and 135 days returning. That complete timeline matters because it asks a harder question. Can the same general geometry support going there and getting home? That is a much stronger claim than only showing a fast outbound leg. Still, the return leg is not gentle. 135 days back is shorter than many conventional mission structures, but it is still a high-stakes deep space journey. The spacecraft has to leave Mars at the correct time, follow the correct path, protect the crew, manage consumables, handle radiation, and arrive at Earth with a survivable re-entry plan. Earth return is not automatic. A spacecraft coming back from a high-energy Mars trajectory may hit Earth's atmosphere at very high speed. That means thermal protection matters again, guidance matters again, entry angle matters again. If the return vehicle arrives too steep, heating and G-load can become dangerous. If it arrives too shallow, it may skip out or miss the right recovery profile. The mission has to end safely, not just quickly, so the 56-day route must be judged as a full system. Outbound speed, Mars arrival, surface stay, Mars departure, return cruise, Earth re-entry, crew health, vehicle mass, propulsion, thermal protection, abort options. Every piece has to close. That is why the word feasible is useful but limited. It tells us this profile is not in the same category as the most extreme 33-day case. It suggests the route may be less punishing and more balanced. But it does not remove the engineering burden. The route may be feasible in trajectory space. The mission may still be very difficult in hardware space. That distinction is the center of this whole topic. A trajectory study can identify a path. It can calculate timings. It can check alignments. It can compare energy demands. It can test whether Earth and Mars can be connected under a certain geometry. But a spacecraft has mass. It has engines. It has tanks. It has heat shields. It has failure modes. It has humans inside if this becomes a crewed mission. Reality is heavier than the line on the trajectory plot, and that is exactly why the 56-day case is compelling. It does not rely only on shock value. It points toward a possible mission class, fast enough to reduce the biggest human duration risks, but not as obviously extreme as the 33-day option. This could affect the way Mars missions are designed. Instead of accepting a long cruise as unavoidable, mission planners could ask whether rare high-speed windows are worth the energy cost. Instead of designing everything around months of transit, they could consider architectures where cargo travels slowly and efficiently, while crews travel faster. Instead of treating the Mars mission as a huge long-duration isolation event, they could explore shorter, sharper expeditions with different risk profiles. That does not mean this is the final answer. It means the design space gets wider. The old question was, how do we survive a long trip to Mars? The new question becomes, is it better to spend more energy so humans spend less time in deep space? That is a serious question, It has no easy answer. More energy can reduce chronic health risk, but it can increase mission event risk. Shorter travel can reduce radiation exposure, but it can also reduce time for checkouts and corrections. Faster arrival can save months, but it can make braking much harder. So the 56-day route is not a miracle. It is a trade with numbers attached. 56 days outbound, 35 days on Mars, 135 days back, 226 days total. Those numbers are still aggressive. They still demand technologies and systems beyond a simple Mars mission. But they're also not as far outside serious discussion as the 33-day case. That is why this section of the story shifts from shock to engineering realism. The 33-day route proves the idea can be dramatic. The 56-day route shows why the idea may be worth studying seriously. And the reason 2031 matters is that this profile does not appear in empty space. It appears because Earth, Mars, and the CA21 derived plane line up in a specific way. Change the year, and the opportunity may weaken or disappear. So the next question becomes unavoidable. Why does 2031 stand out so strongly? And why does a single alignment between two moving planets and one asteroid-derived plane change the whole mission? 2031 matters because Mars is not just close enough. The path is lined up enough. That is the difference most people miss. Every 26 months or so, Earth and Mars reach a useful arrangement called opposition. Earth passes between the Sun and Mars, and the two planets end up on the same general side of the solar system. This is why Mars launch windows repeat again and again. The planets move at different speeds. Earth catches up and mission planners get another chance. But opposition does not automatically create a shortcut. It only creates a starting condition. Mars can be nearer to Earth and still be difficult to reach fast. A spacecraft still has to leave Earth in the right direction, arrive at Mars at the right moment, match the correct plane, handle the right transfer angle, and return at the right time. Distance is only one part of the problem. A close Mars is not the same thing as an easy Mars. That is why 2031 is important. The study did not simply say Mars opposition happens, so launch then. It looked at multiple future opposition periods, including 2027, 2029, and 2031. Those years all offered Earth-Mars timing opportunities, but they were not equal. The CA21 derived geometry had to be tested against each one, and 2031 stood out. The reason is not magic. It is not because Mars suddenly becomes easy. It is because three things line up better than usual: Earth's position, Mars's position, and the asteroid-derived transfer plane. That third part is the key. Most people think of a Mars window as only the planets being in the right place, but for a spacecraft, the angle of the path also matters. The spacecraft moves in a plane around the Sun. If that plane is badly tilted compared with the useful transfer geometry, the spacecraft has to spend energy correcting the angle. That correction can become expensive fast. This is called a plane change penalty, and it is one of the quiet killers of mission design. Changing orbital inclination means changing the tilt of the spacecraft's path. That takes velocity, and velocity change means delta V. Delta V means fuel. Fuel means mass. Mass means bigger launch vehicles, smaller payloads, or a mission that stops making sense. So when a route already matches a useful plane, that is a major advantage. The CA21 derived method matters because it searches for a moment when the spacecraft does not have to fight the plane as much. In 2031, the alignment reportedly minimizes plane change penalties and gives a more balanced outbound and inbound route. That is why this is not just a story about Mars being nearby. The route works because the timing and the plane cooperate. That is a much stronger idea. A planet being close is helpful. A planet being close while also matching a useful transfer plane is far more important. And a return opportunity fitting into the same general architecture makes it even more serious. This is why ordinary wait for Mars opposition thinking is not enough. Opposition tells you when the Earth and Mars are on the same general side of the Sun. It does not tell you whether a 33-day transfer is practical. It does not tell you whether a 56-day transfer has a better energy balance. It does not tell you whether the return leg can fit. It does not automatically solve inclination, arrival velocity, or departure energy. A shortcut needs more than closeness. It needs agreement. The planets must be in useful positions. Their relative motion must support the timing. The spacecraft's path must avoid expensive plane changes. The Mars arrival must be possible. The Earth return must not break the mission. That is a much tighter filter than simply saying Mars is near. This is why 2027 and 2029 did not become the main headline in this study. They may have had Mars opposition opportunities, but they did not match the CA-21 derived plane as favourably. The geometry was not as useful. The penalty was higher. The route was not as balanced. Then 2031 appears. That is the moment where the asteroid clue becomes more than a strange data point. It becomes a possible mission window. The spacecraft can use a path close to the CA-21 derived plane. Staying near that plane reduces the need for major sideways correction. That matters because sideways correction in space is not cheap. A rocket engine does not care whether it is speeding up, slowing down, or tilting the path. It still spends propellant. Every correction adds mass pressure to the mission. And for a fast Mars transfer, there is already enough pressure. The spacecraft is leaving Earth fast, it is crossing interplanetary space fast, it is arriving at Mars fast. It may need advanced braking, it may need a strong return plan, it cannot afford to waste large amounts of energy just fixing a bad plane angle. So 2031 matters because it reduces one of the major penalties. Not all of them, just one of the big ones. That is important to say clearly. The 2031 window does not make the route easy. It does not erase the rocket equation. It does not solve aerocapture. It does not build a propulsion system. It does not guarantee safe entry, landing, or return. But it does give the trajectory concept a better chance because the geometry is less hostile. That is the real meaning of a good window. A good launch window does not remove the difficulty of Mars. It reduces the number of things working against you. And in 2031, according to this CA-21-based search, fewer things are working against the rapid transfer. Earth and Mars are positioned in a way that makes the asteroid-derived plane useful. The outbound and inbound arcs become more balanced. The plane change penalties become lower. The route becomes mathematically more attractive. That is why the year matters, but the danger is that people hear 2031 and think it's a scheduled mission date. It is not. It is a trajectory opportunity. That means the geometry may be favourable in that year. It does not mean the spacecraft exists. It does not mean the crew is assigned. It does not mean the mission is approved. It does not mean the propulsion and braking systems are ready. A window is not a mission. A window is a chance, and chances expire. That is one of the harshest parts of interplanetary travel. On Earth, if a road is open, it usually stays there. In space, the route changes because the planets keep moving. A path that works in 2031 may not work in 2033. A fast transfer that fits one alignment may become too expensive in the next. The solar system does not wait. So a 2031 opportunity has to be understood as time-sensitive geometry. The planets move into position. The useful plane becomes valuable. Then the planets move on. The opening closes. That makes this story more urgent, but also more grounded. It is not saying humans must launch in 2031. It is saying the model found a specific year where the CA-21 derived route becomes unusually promising. That is exactly what a trajectory search is supposed to do. It filters through time and finds the moments when the math becomes less impossible. And that is where asteroid-inspired trajectory mining becomes important. Traditional Mars planning already knows about the 26-month rhythm. That rhythm is real and useful, but asteroid-derived searches may reveal which of those windows have extra hidden advantages. One opposition may be ordinary. Another may be unusually aligned with a plane suggested by small-body data. Another may allow a return arc that is less punishing. Another may fail completely. So the question changes. Not just, when is Mars close? But, which Mars window has the right complete geometry? That is a much more powerful question, because a useful Mars opportunity depends on relative position, relative velocity, transfer angle, inclination, arrival geometry, return timing, and energy balance. All of those variables interact. A shortcut appears only when enough of them line up at the same time. That is why 2031 is special in this story. It is not special because of a calendar number. It is not special because the planets decide to make Mars easy. It is special because the CA21-derived plane, Earth's position, and Mars's position create a rare alignment that makes rapid transfer profiles possible in the model. The planets are still moving targets, the spacecraft still pays for speed, the arrival problem still waits at Mars. But for this particular window, the geometry gives the mission a better opening. And once that opening appears, the next question becomes the most unforgiving one in all of rocketry. How much energy does the shortcut actually cost? A shortcut to Mars does not remove the cost of travel, it moves the cost into speed. That is the hard rule underneath this entire story. In orbital mechanics, saving time usually means spending energy. A spacecraft that reaches Mars in 56 days or 33 days is not doing the same job as a slow transfer. It is leaving Earth with more speed, crossing space on a more energetic path, and arriving at Mars with more velocity that must be removed. That is the bill. And the bill is paid in delta V. Delta V means the amount of velocity change a spacecraft needs to perform a mission. It is one of the most important numbers in spaceflight. If a spacecraft needs to speed up, that costs delta V. If it needs to slow down, that costs delta V. If it needs to tilt its path, that costs delta V. If it needs to correct its course, that also costs delta V's. So when a trajectory promises a much faster trip, the first serious question is not, how many days does it save? The first serious question is, how much delta V does it demand? That is where the CA21 shortcut becomes difficult. A fast Mars route may reduce time in deep space, but it is not automatically cheaper. In fact, it may be much more expensive in energy. That matters because propellant is one of the biggest limits in mission design. More propellant means more mass. More mass means a bigger rocket, fewer payload options, more launches, or a mission that stops being realistic. This is why mission planners usually care so much about minimum energy paths. They are not choosing slow routes because they like waiting. They choose them because launch vehicles have limits. Spacecraft have mass limits. Budgets have limits. Every kilogram has to be justified. So the asteroid-derived shortcut has to face the same question every mission faces. Can the spacecraft actually pay the energy price? The first payment comes at departure. To reach Mars much faster than a Hohmann-style transfer, the spacecraft must leave Earth with extra speed beyond a standard trans-Mars injection. That extra departure energy is not a small detail. It can change the entire launch architecture. A normal Mars transfer already requires a powerful launch. A fast transfer can require far more. That may mean using a much larger launch vehicle. It may mean assembling the spacecraft in Earth orbit. It may mean refueling in orbit before departure. It may mean using nuclear thermal propulsion. It may mean sending cargo ahead slowly while the crew vehicle uses the fast route later. It may mean stage systems, where one part of the vehicle gives the spacecraft its departure push and is then discarded. None of this is impossible in principle, but none of it is simple. A fast Mars mission needs more than a clever path. It needs a propulsion system that can put a real spacecraft with real mass onto that path. And for a crewed vehicle, the mass is not small. You need a habitat, radiation shielding, life support, power, communication, navigation, spare parts, medical systems, and margins for failure. The faster route is not just carrying a capsule. It is carrying a survival system. That is why departure energy matters so much. A tiny robotic probe can be accelerated more easily than a crewed Mars ship. But a human spacecraft is heavy. If the shortcut requires very high departure speed, the launch system becomes a central problem. The route may look clean in trajectory math, but the rocket has to deliver the mass. And after departure comes the bigger problem: Mars arrival. This is where fast Mars transfers become dangerous. The spacecraft reaches Mars with high speed relative to the planet. That speed has to be reduced. If it is not reduced, the spacecraft does not enter orbit and does not land. It just flies past Mars. A slow transfer already needs braking. A fast transfer needs much more serious braking. There are only a few ways to remove that speed. The spacecraft can fire engines and burn propellant. It can use the Martian atmosphere to slow down, or can use a combination of both. Each option has consequences. If the spacecraft uses engines, it must carry the propellant needed for Mars capture. That propellant had to be launched from Earth or produced and staged somewhere else. Carrying it makes the spacecraft heavier. A heavier spacecraft needs more energy to depart Earth. That can make the whole mission grow rapidly. If the spacecraft uses the atmosphere, it can save propellant, but it faces heat, force, and guidance risk. Mars has an atmosphere, but it is thin and variable. It can slow a spacecraft, but it can also punish a high-speed entry. The faster the spacecraft arrives, the more intense the heating can become. The vehicle may also face higher G loads, sharper control demands, and a smaller margin for error. That is why aerocapture becomes important in this discussion. Aerocapture could allow a spacecraft to use the Martian atmosphere to turn a high-speed arrival into a captured orbit. That could reduce the propellant needed for Mars orbit insertion. But aerocapture at high speed is not a casual maneuver. It requires an accurate arrival corridor, a strong heat shield, reliable control, and a clear understanding of the Martian atmosphere at that moment. For a crewed mission, the standard is even higher. The vehicle cannot simply survive once in a lucky test. It must perform reliably with humans on board. So the faster the shortcut becomes, the more Mars arrival becomes the main obstacle. That is the uncomfortable truth. A 33-day or 56-day trip sounds like it solves the travel time problem. But it may hand the engineers a much harder braking problem. The spacecraft saves time during cruise, then pays for that time at Mars, and the payment can be massive. This is where the rocket equation becomes unavoidable. You do not need to see the equation to understand the problem. A spacecraft needs propellant to change speed. Propellant has mass. If you add more propellant, the spacecraft gets heavier. If the spacecraft gets heavier, it needs even more propellant to move the added mass. This creates a growth problem. The mission can quickly become too heavy for the launch system. That is the mass trap. And every fast Mars concept must escape it. The important question is not only whether the path exists, the question is how much useful payload reaches Mars after all the propulsion demands are counted. If the spacecraft uses most of its mass just to accelerate and brake, then the mission may not carry enough habitat, shielding, cargo, science equipment, or return capability. A fast route that delivers almost no useful mass is not a useful mission. That is why flight time alone can mislead people. A 33-day transfer sounds better than a 259-day transfer. But if the 33-day transfer requires impossible propulsion, impossible braking, or a spacecraft too massive to launch, then it is not better. It is just more aggressive on paper. The real comparison is not days versus days. It is days versus energy, mass, risk, and survival. A mission designer has to ask hard questions. How much departure speed is needed? How much propellant is required? What launch vehicle can provide it? Can the spacecraft be refueled in orbit? Can the vehicle survive Mars arrival? Can the crew survive the G loads? Can the heat shield handle the entry? Can the spacecraft enter orbit instead of flying past? Can it land? Can it return? Can Earth re-entry be survived after a high-energy return? Every answer affects the next answer. That is why new launch systems matter. The CA-21-derived route becomes more relevant if the supporting technology improves. Heavy-lift rockets can place more mass into orbit. Orbital refueling can allow a spacecraft to launch dry or partially fueled, then fill up before departure. Nuclear thermal propulsion could provide higher performance for crewed deep space missions. Solar electric propulsion could pre-position cargo or stages. High-performance aerocapture could reduce the propellant needed at Mars. With those technologies, a high-energy Mars route becomes more than a mathematical result. Without them, it may remain only a trajectory opportunity. That is not a weakness of the science. It is the normal gap between astrodynamics and mission architecture. The trajectory can show where a path exists. Propulsion decides whether a real spacecraft can use it. Thermal protection decides whether it can arrive. Life support decides whether humans can survive the timeline. Navigation decides whether the vehicle can hit the narrow target. The shortcut expands the menu, it does not cook the meal. And that is the grounded way to understand the CA21 result. It may reveal a special path. It may show that 2031 has a fast Earth-Mars-Earth geometry. It may point to a 56-day outbound route and an extreme 33-day outbound route. But the route still has to survive the rocket equation. If the energy demand is too high, the shortcut stays theoretical. If propulsion, refueling, launch capacity and aerocapture improve, the shortcut becomes more serious. That is the real dividing line. Not whether the trajectory is exciting, it is. Not whether the math is interesting, it is. The question is whether the spacecraft can carry enough mass, move fast enough, slow down safely and still complete the mission. Until that closes, the shortcut is not a replacement for standard Mars transfers. It is a new candidate in a much larger design space. And that larger design space includes a completely different strategy. Instead of getting to Mars faster by spending more energy, some missions try to reach Mars by spending less energy and accepting a slower, more subtle capture process. That is the opposite side of the Mars travel problem. The fastest way to understand the Mars shortcut is to compare it with the opposite strategy. The CA21 route is a high-speed idea. It tries to cut travel time by using a rare geometry, higher departure speed, and a more aggressive Earth-Mars path. It is about getting there faster, even if the spacecraft has to pay a higher energy price. Ballistic capture works in a very different way. Ballistic capture is not about racing to Mars. It is about arriving in a way that makes capture easier. Instead of flying straight into a hard Mars orbit insertion burn, the spacecraft approaches the gravitational environment around Mars more gently under the right conditions. It can become captured far from Mars first, then move inward later. That is the opposite trade. The CA21 shortcut may save time. Ballistic capture may save insertion energy. And that difference matters because shortcut does not always mean the same thing in spaceflight. On Earth, a shortcut usually means a shorter road. In space, a shortcut can mean many different things. It can mean less travel time. It can mean less fuel. It can mean lower arrival energy. It can mean more flexible launch dates. It can mean less risk during one part of the mission, even if another part becomes harder. So when someone says shortcut to Mars, the first question should be, shortcut in what sense? The CA21 idea is a time shortcut. It tries to reduce the number of days between Earth and Mars. But ballistic capture is closer to an energy shortcut. It may take longer, but it can reduce the velocity change needed to become captured by Mars under certain conditions. This is not the same mission style. A fast CA21 transfer could arrive at Mars with high speed and then face a difficult braking problem. Ballistic capture tries to avoid a harsh capture burn by using the natural gravitational structure around Mars. The spacecraft does not slam into a tight orbit right away. It can first enter a weakly captured state farther out, then gradually transfer inward. That can reduce the amount of propellant needed for capture. But again, there is a trade. Ballistic capture can be slower. It can require more complex navigation. It may not fit every mission timeline. It may not be ideal for crews who need to reduce time in deep space. But for robotic spacecraft, cargo, or pre-positioned supplies, it can be valuable. A robot does not care if the trip takes longer. Cargo does not get bone loss. A fuel depot does not suffer radiation sickness. That is why this comparison is important. The future of Mars travel may not use one single route. It may use different route types for different jobs. Crew may need speed, cargo may need efficiency, science probes may need launch flexibility, return vehicles may need careful staging. Each mission has a different priority, and this is where Mars mission design becomes more interesting than the simple textbook picture. The textbook picture says you use a Hohmann transfer because it is efficient. You wait for the correct window, launch, coast for months, and arrive. That is the clean classroom version. But real mission design has more options. There are high energy transfers, there are low energy transfers, there are gravity assists, there are ballistic capture paths, there are low thrust spirals, there are resonant trajectories, there are asteroid-derived search methods like CA-21, there are routes that save fuel but take longer, there are routes that save time but demand more propulsion. The solar system is not simple, and that is exactly why new methods matter. Ballistic capture is tied to something called the weak stability boundary. The phrase sounds difficult, but the basic idea is simple. Around planets, there are regions where the pull of the planet, the pull of the sun, and the motion of the spacecraft interact in a delicate way. In these regions, small changes in speed or direction can decide whether a spacecraft is captured, escapes, or moves into a different kind of orbit. That is why these regions matter. They are not physical tunnels, they are not roads, they are not lines painted in space, they are dynamical conditions. They are places in the motion of the spacecraft where gravity can be used carefully, and careful use of gravity can save fuel. This idea has been studied for lunar and interplanetary missions. It is not science fiction, it is real astrodynamics. The spacecraft still obeys gravity, it still needs precise navigation, it still may need correction burns, but it uses the structure of the gravitational environment instead of fighting it directly. That is the key contrast with the CA-21 transfer. The CA-21 route says, use geometry to go fast. Ballistic capture says, use gravity to reduce capture cost. And both ideas are different from the simple point-and-shoot idea most people have about Mars travel. Both show that interplanetary motion is richer than a basic two-body orbit around the Sun. Real spacecraft are influenced by the Sun, planets, timing, speed, inclination, and the exact arrival conditions. That is why the old idea of one standard Mars route is too limited. A Hohmann transfer is useful, it is efficient, it is a major baseline, but it is not the whole story, it is one family of solutions. The CA-21 results suggest there may be rare fast transfer families. Ballistic capture suggests there may be low-energy capture families. Other methods use gravity assists, low thrust or resonances. The mission designer's job is to choose the right tool for the mission. For a crewed Mars mission, time matters a lot. Radiation exposure matters, microgravity matters, psychological stress matters, life support duration matters. A fast route can help with those problems. That is why a 56-day outbound transfer is so attractive. But for cargo, time may matter less. A habitat module, a power system, a rover, a spare ascent vehicle, or a propellant tank can travel slowly if that saves mass. If ballistic capture reduces the fuel needed to enter Mars orbit, that may be more useful than speed. This leads to a more realistic future architecture. Send cargo slowly and efficiently. Send crew faster when the window allows. Use aerocapture where it makes sense. Use ballistic capture where it saves mass. Use asteroid-derived geometry to identify rare high-speed windows. Use different methods for different parts of the campaign. That is much more realistic than expecting one route to solve everything. And this also changes how we judge the CA-21 shortcut. It does not have to replace every Mars transfer. It does not have to become the universal way to reach Mars. It only has to add a new option to the mission design toolbox. If it works for a specific 2031 opportunity, or for future windows found through asteroid data, then it becomes valuable. A route can be valuable even if it is not always usable. That is how interplanetary mission design already works. Some trajectories only exist during specific alignments. Some gravity assists only work when planets are in the right positions. Some launch windows are better for heavy cargo. Some are better for fast crew transfer. Some are better for sample return. The CA-21 route fits that same logic. It is not a permanent road to Mars. It is a possible high-speed opportunity found through a specific geometry. Ballistic capture gives the other side of the same lesson. It shows that Mars arrival does not always have to be handled with a huge engine burn. Under the right conditions, the spacecraft can exploit the gravitational environment and reduce capture energy. That does not make it easy. It makes it different. And different is exactly what Mars mission planning needs. Because the standard problem is severe. Slow transfers expose crews to deep space for months. Fast transfers demand more energy and harder braking. Direct capture requires propellant. Atmospheric braking creates heat and control risk. Long surface stays create logistics problems. Short surface stays create schedule pressure. Every option has a cost, so the future will likely be built from combinations, not one perfect answer. A rapid crew mission might use a high-energy transfer, then aerocapture at Mars. Cargo might use low-energy trajectories or ballistic capture. Return vehicles might be pre-positioned. Propellant might be sent ahead. Nuclear thermal propulsion might reduce flight time. Solar electric propulsion might move cargo efficiently. Asteroid-derived searches might reveal special windows that the planners would otherwise miss. That is why this section matters. It keeps the Mars shortcut story honest. The CA-21 discovery is not saying fast is always better. It is saying fast may be possible in a rare geometry. Ballistic capture reminds us that other missions may care more about saving fuel than saving time. Both are valid, both are tools. Both show that space travel is not limited to one simple transfer curve. That is the bigger shift. Mission designers are no longer limited to textbook Mars transfers. They can search real ephemeris data. They can mine asteroid orbits. They can use Lambert solvers. They can test low energy capture. They can use gravity assists. They can exploit resonances. They can plan low thrust arcs. They can compare many route families instead of relying on one standard answer. The solar system is becoming a navigable, dynamical system. Not easy, not safe by default, not open without cost, but more searchable than it used to be. And once you understand that, the CA-21 shortcut becomes part of a larger pattern. Nature is not giving spacecraft free rides, but gravity, timing, and orbital geometry create opportunities. Some opportunities save fuel, some save time, some create safer arrival conditions, some create more flexible launch windows, some are too extreme for current technology, but still useful because they show what might become possible later. That leads to the next major piece of the puzzle. Because before CA-21, before ballistic capture, before low-energy pathways, mission designers already used another powerful tool to reshape spacecraft routes. They used planets themselves. And this is where gravity assists and resonances reveal that the solar system has a much deeper structure than a simple path from Earth to Mars. The next major clue is this. Spacecraft have already been using planetary motion to change their speed for decades. That is gravity assist. A gravity assist happens when a spacecraft flies close to a planet and uses that planet's gravity and motion to change its own path. The spacecraft can leave the encounter faster, slower, or in a different direction, depending on how it approaches. It sounds like free energy, but it is not free. The spacecraft is taking a tiny amount of energy from the planet's motion around the Sun, or giving a tiny amount back. For the planet, the change is basically impossible to notice. For the spacecraft, it can decide the entire mission. This is how missions reach places that would otherwise require much more fuel. A spacecraft can use Venus, Earth, Jupiter, or other planets to reshape its route. It is not cheating physics. It is using physics with precision. The spacecraft falls into the planet's gravity field, swings around it, and leaves with a changed speed relative to the Sun. That one maneuver can open a mission that a direct launch could not handle. So the solar system is not just a set of destinations, it is a moving system of energy exchanges. Planets are not only targets, they can be tools. Their gravity and motion can redirect spacecraft in ways that rockets alone might struggle to do. And this connects directly to asteroid trajectories. The CA-21 shortcut is not a gravity assist off the asteroid. That must be clear. The asteroid is not pulling the spacecraft to Mars, it is not giving the spacecraft a boost. Most asteroids are too small for that. Their gravity is far too weak to act like a planet. The asteroid is useful because its orbit points to a pattern. Asteroids move through the solar system for long periods under the pull of the Sun and planets. Their paths are shaped by the repeated gravitational effects, near misses, resonances, and slow changes over time. So when scientists track asteroids, they are also tracking how gravity naturally moves small bodies. That is why asteroid orbits can become clues. They show where objects have been able to travel. They show which inclinations, timings, and crossings exist in the real solar system. Some asteroid paths cross near Earth. Some pass near Mars. Some are pushed inward from the asteroid belt. Some are shaped by Jupiter. Some end up in near-Earth space because repeated gravitational interactions change their orbits over long times. A spacecraft is not an asteroid, but it moves through the same gravitational environment. That is the important point. If asteroid data shows a certain kind of orbit repeatedly passing through useful regions, mission designers can ask whether a spacecraft can use a related path, not by copying the asteroid perfectly, not by flying next to it, but by using its orbital elements as a search clue. That is what makes the CA21 idea different from a standard Mars transfer search. Instead of starting only with the planets and asking for normal transfer arcs, the method starts with an asteroid-derived plane and asks whether Earth and Mars can be connected near that plane during a future window. It uses small body data as a filter. It narrows the search toward geometries that nature has already placed into the database. That does not guarantee a good route. It just gives the search a direction. And in trajectory design, that matters because the number of possible routes is enormous. Change the departure date, and the route changes. Change the arrival date, and the route changes. Change the flight time, and the required energy changes. Change the plane, and the delta V changes. Add a return leg, and the problem becomes even more complex. So any useful filter matters. Asteroid trajectories can provide that filter because many of them are connected to resonances. A resonance happens when orbital periods line up in repeated ratios. In simple terms, one object keeps meeting the same gravitational influence again and again at regular timing. Those repeated pulls can build up over time. They can move asteroids from one region into another. They can pump up an orbit, tilt it, stretch it, or push it into a planet-crossing path. This is one way objects from the asteroid belt can eventually become near-Earth objects. Jupiter is especially important here because it is massive. Its gravity can disturb asteroid orbits over long periods. But other planets matter too. The result is that asteroid populations are not random clouds of rocks. Their orbits carry the history of gravitational routing. That is why the phrase, "inspired by asteroid trajectories," makes scientific sense. Asteroids already show how small bodies move under repeated gravitational influence. Their paths are not designed, but they are real. They are outcomes of the solar system's dynamics. If those outcomes include paths that pass through Earth's neighbourhood and Mars's neighbourhood, then those paths are worth examining. Again, this does not mean there is a physical road to Mars. There is no lane, no tunnel, no permanent track. A better way to say it is this. There can be a favourable corridor in the mission design search space. That means a set of positions, speeds, inclinations, and timings where the required transfer becomes more attractive than usual. The CA21 derived route is a corridor in that technical sense. It is not a road sitting in space. It's a combination of plane alignment and timing that reduces some penalties. The spacecraft still needs propulsion. It still needs navigation. It still needs braking. It still has to survive the mission. But the geometry may be less hostile, and that is enough to matter, because mission design is often about reducing penalties one by one. Reduce the plane change penalty, reduce the departure energy if possible, reduce the arrival energy if possible, reduce the time in radiation, reduce the mass, reduce the number of risky burns, reduce the number of things that must go perfectly at once. A useful corridor does not solve everything. It only makes one version of the problem less punishing. Gravity assists work the same way in a broader sense. A planet flyby does not make the mission easy. It changes the energy and direction in a useful way. Resonances do not create magic paths. They create repeated timing relationships that can be exploited. Ballistic capture does not erase braking. It can reduce capture energy under the right conditions. The CA-21 method does not build a spacecraft. It reveals a candidate geometry. All of these are different ways of using the structure of motion. That is the bigger mission design revolution. Modern spacecraft routing is no longer limited to a clean Hohmann transfer drawn in a simple diagram. Those diagrams are useful, but they are the beginning, not the end. Real mission design now uses planetary ephemerides, asteroid catalogues, Lambert solvers, gravity assist searches, low-thrust optimization, resonant returns, ballistic capture methods, and massive computer searches across thousands or millions of options. The search space is too large for simple intuition. Computers can test combinations that a human planner would not manually check one by one. They can vary dates, flight times, inclinations, velocities, and encounter conditions. They can reject impossible paths and highlight strange ones. They can search asteroid databases for unusual planes. They can connect real planet positions to possible spacecraft arcs. That is why CA-21 is not just a Mars story, it is a search space story. The results suggest that useful mission opportunities may be hidden inside datasets that were not originally built for mission design. Near-Earth asteroid catalogues were built mainly for tracking and defense, but because they contain real orbital pathways, they can also be searched for transfer clues. That is a major shift. The same data that helps answer, could this asteroid become a threat, may also help answer, does this orbit reveal a useful path? That does not mean every asteroid becomes a mission route. Most will not, but with enough objects, enough orbital solutions, and enough computation, rare alignments can be found. And rare alignments are exactly what deep space missions need. A single good window can define a mission. A single gravity assist can make a mission possible. A single plane match can reduce a major cost. A single return alignment can turn a one-way concept into a round-trip architecture. That is why mission designers care about more than distance. They care about timing, speed, plane energy, and return geometry. They care about how all of those variables combine. They care about whether the route can actually close as a complete mission. The CA-21 route enters that world as one more tool. Not proof that Mars is suddenly easy, not proof that a 33-day crewed mission is ready, but proof that asteroid-derived trajectory searches can expose options that simple textbook planning may not show. And this is where the story gets more serious. Because once you accept that the solar system can be searched this way, the next obstacle becomes unavoidable. Finding a fast route is not enough. Reaching Mars is not enough. Matching the plane is not enough. The spacecraft still has to arrive, and for a high-speed Mars transfer, arrival is where the mission can fail in minutes. Reaching Mars fast is not the victory. Slowing down is the test that can destroy the mission. That is the brutal part of a high-speed transfer. The spacecraft may cross space in 56 days or even 33 days, but when it reaches Mars, it is not finished. It is still moving extremely fast relative to the planet. If it cannot remove that speed, it cannot enter orbit. It cannot land. It cannot support a surface mission. It just flies past Mars and the entire mission becomes a high-speed failure. This is why arrival is the bottleneck. A slow Mars transfer already has to deal with braking. A spacecraft arriving at Mars must decelerate relative to the planet. For an orbiter, that usually means a Mars orbit insertion burn or some form of atmospheric braking. For a lander, it means entering the atmosphere, surviving heat, slowing down, deploying systems, and using engines or other devices before touchdown. That is already hard with standard Mars missions. A rapid CA-21 style transfer makes it harder. The faster the spacecraft gets to Mars, the more speed it must remove at arrival. That speed is not just a number on a chart. It becomes heat. It becomes stress. It becomes propellant demand. It becomes guidance pressure. It becomes risk concentrated into a short period of time. This is the part that makes the shortcut dangerous to oversell. The route may solve the time problem, but it creates a braking problem. Mars makes that braking problem especially difficult because its atmosphere is in an awkward middle zone. Mars has enough atmosphere to create dangerous heating during entry, but it does not have enough atmosphere to make landing easy. Earth's atmosphere is thick enough to slow spacecraft strongly. The Moon has almost no atmosphere, so you use engines. Mars sits in between, and that makes it one of the hardest places to land. The atmosphere helps, and the atmosphere hurts. It helps because it can reduce the amount of propellant needed. If the spacecraft can use atmospheric drag, it can slow down without burning as much fuel. That is why heat shields, parachutes, and aerodynamic braking matter so much at Mars. But it hurts because high-speed entry turns the atmosphere into a violent environment. The spacecraft compresses the gas in front of it. The temperature rises. The heat shield takes the punishment. The vehicle must stay stable. The guidance system must keep the entry angle correct. The structure must survive the loads. If the spacecraft is crewed, the G-forces must stay within human limits. A faster arrival makes all of this more severe. That is why a conventional entry system may not be enough for a rapid transfer. A spacecraft arriving from a normal trajectory already faces intense entry conditions. A spacecraft arriving from a high-energy 33-day or 56-day path may need a very different arrival architecture. And this is where mission design becomes much more than choosing a path. There are several ways to handle Mars arrival, and each one changes the mission. One option is orbit insertion with engines. The spacecraft fires its propulsion system to slow down and enter orbit around Mars. This gives control, but it costs propellant. For a high-speed arrival, the required burn could become very large. That means the spacecraft must carry more fuel all the way from Earth, which makes it heavier, which makes departure harder. Another option is direct entry. A lander enters the atmosphere and goes straight toward the surface. This can work for robotic payloads, and it has been used many times in different forms, but for a large crewed spacecraft arriving at high speed, direct entry becomes much more dangerous. You have less room for error, more heating, more stress, and a very compressed timeline. A third option is aerocapture. Aerocapture is one of the most important ideas in this discussion because it attacks the braking problem directly. Instead of using engines to remove all the arrival speed, the spacecraft uses one controlled pass through the Martian atmosphere to slow down enough to become captured into orbit. In simple terms, the spacecraft arrives on a path that would normally fly past Mars. It dips into the atmosphere, loses speed to drag, then exits the atmosphere in a bound orbit around the planet. That could save a huge amount of propellant. But it is also extremely demanding. The spacecraft must hit the atmosphere with very high precision. If it enters too shallow, it may not slow down enough and could escape back into space. If it enters too steep, heating and G-loads can become dangerous. The vehicle must survive the thermal pulse, control its lift or drag, and come out at the correct speed and direction. For a high-speed CA-21 transfer, aerocapture becomes more valuable because the propellant savings could be massive, but it also becomes more punishing because the arrival speed is higher. Higher speed means higher heating, tighter targeting, and less tolerance for mistakes. That is the central trade. Aerocapture could make a fast Mars mission more realistic. Aerocapture could also become one of the highest risk phases of the mission, and for humans, that risk becomes a major obstacle. A robotic spacecraft can be sent to test a dangerous technique. If it fails, the mission is lost, but no crew dies. A human mission cannot be treated that way. Crewed aerocapture would need a level of confidence that comes only after serious testing, modelling, and probably robotic demonstrations. That is why a rapid Mars mission would likely need a step-by-step arrival plan. A crewed vehicle might not go straight from interplanetary space to the surface. A safer architecture may involve aerocapture into Mars orbit first. Then the crew checks systems, then they verify the spacecraft is healthy, then they transfer to a lander or descend in a controlled way. That adds complexity, but it may reduce the risk compared with direct high-speed entry. But complexity has a cost too. An orbiter needs systems. A lander needs systems. Docking or transfer operations need time. Mars orbit operations need life support and power. Every added part increases mass and failure modes. So arrival architecture cannot be separated from the shortcut. The shortcut and the braking system are one combined problem. This is the mistake people make when they focus only on flight time. They hear 33 days to Mars and think the problem is the journey. But the true mission problem is Earth departure plus cruise plus Mars arrival plus surface operations plus return plus Earth re-entry. If one phase becomes impossible, the whole architecture fails. Mars arrival may be the phase that decides everything. The atmosphere changes from helpful to dangerous depending on speed and angle. The engines change from backup systems to mission-critical braking systems depending on the design. The heat shield changes from standard protection to one of the most important technologies in the mission. Navigation changes from routine correction to a life or death targeting problem. And the faster the route, the less forgiving the arrival becomes. A small navigation error can become a bad entry angle. A bad entry angle can become too much heating or not enough braking. Not enough braking can mean missing capture. Too much braking can mean unsafe G-loads or vehicle loss. Mars atmospheric density can also vary, and that matters because aerocapture depends on how much drag the spacecraft experiences. So engineers would need strong margins, they would need accurate Mars atmosphere models, they would need reliable onboard guidance, they would need a heat shield designed for high-energy arrival, they would need backup options if the vehicle comes in slightly off target. They would need to know whether the crew can survive the forces. They would need to know whether the vehicle can still perform after the heating event. This is why the 33-day route is so hard to take as a near-term crewed mission. It compresses the cruise, but it makes the arrival extremely severe. The 56-day route may reduce the violence compared with 33 days, but it still requires serious braking technology. It is still not a normal Mars arrival, and even after capture, the spacecraft is not done. If the vehicle enters Mars orbit, it still has to support the crew. It has to prepare for descent or rendezvous. It has to maintain communication. It has to handle any damage or stress from aerocapture. If the mission includes landing, the crew still has to get from orbit to the surface safely. That descent is its own challenge. The shortcut only counts if the spacecraft becomes useful at Mars. A flyby is not enough for a human landing mission. A near miss is not enough. A high-speed arrival is not enough. The spacecraft must convert interplanetary speed into a stable orbit or a safe landing. That conversion is the real test. And this is also why robotic testing would be so important before any human attempt. A small spacecraft could test the arrival speed, navigation, heating and aerocapture profile without risking a crew. Then a larger demonstrator could test higher mass systems. Only after that would a crewed architecture make sense. Because Mars does not care how elegant the transfer math is. The planet only cares about the physics of arrival. Too fast and you burn or miss. Too slow to correct and you fail the capture. Too much reliance on engines and the spacecraft becomes too heavy. Too much reliance on atmosphere and the heat shield becomes the mission's weak point. That is the arrival trap. The CA-21 route may reduce travel time in a dramatic way, but it does not remove the need to brake. In fact, the faster the route becomes, the more braking dominates the mission. This is why the Mars shortcut cannot be judged as a line from Earth to Mars. It has to be judged as a complete arrival system. The route may solve the time problem, but it hands engineers a braking problem. And once humans are placed inside that spacecraft, the question becomes even more serious. A shorter trip may reduce radiation and microgravity exposure, but it also increases pressure on every system, every correction, and every decision. So the next question is not only whether the spacecraft can survive, it is whether the crew becomes safer overall, or whether the shortcut simply trades one kind of danger for another. A shorter Mars trip could protect the crew from one danger, while pushing them toward another. That is the human side of this shortcut. Faster travel is not only about breaking a speed record. For a crewed Mars mission, time itself is a hazard. Every extra day in deep space means more radiation exposure, more time in microgravity, more strain on life support, more isolation, more chances for equipment failure, and more pressure on the crew. So when a route cuts the outbound trip from about 259 days to 56 days, that is not just a schedule improvement. That could change the health risk. Deep space is not like low Earth orbit. Astronauts near Earth are still partly protected by Earth's magnetic field. A Mars crew is far outside that protection for most of the journey. They face galactic cosmic rays, which are high-energy particles coming from outside the solar system. They also face solar particle events, which can happen when the Sun releases bursts of energetic particles. The longer the crew stays in deep space, the more exposure they collect. That is why rapid transfers are so attractive. A 56-day outbound cruise gives the crew far less time in that environment than a normal months-long cruise. A 33-day outbound cruise would reduce that time even more. Less time in deep space could mean a lower total radiation dose, less damage to the body, and less shielding mass needed for the same risk target. But the trade is not simple. Radiation risk is not only about how many days the crew is in space. It also depends on solar activity, shielding design, spacecraft layout, storm shelter protection, and mission timing. A shorter mission during a dangerous solar event can still be risky. A longer mission with better shielding and better timing may manage risk differently. So fast travel helps, but it does not magically solve radiation. It reduces one part of the problem. It may increase others. A high-energy route may have less abort flexibility. If something goes wrong after departure, the crew may not have many easy options. The spacecraft is moving fast, the timeline is compressed, and the Mars arrival is coming quickly. On a long cruise, the crew has more time to diagnose certain problems, repair systems, and plan corrections. On a rapid transfer, the mission is moving toward its hardest phase almost immediately. That is the paradox. Less time in danger, but less time to react. This also applies to microgravity. During a long Mars cruise, the human body changes. Muscles weaken because they are not working against gravity. Bones lose density. Fluid shifts affect the cardiovascular system. Balance and coordination can change. The crew may arrive at Mars weaker than when they left Earth. That is a serious problem because Mars arrival is not a rest day. The crew may need to handle landing operations, emergency procedures, surface activation, habitat checks, suit operations, rover operations, science work, and preparation for return. If they arrive after 8 months in microgravity, their bodies may not be at peak condition. They may need recovery time. They may need careful adaptation before demanding surface work. A shorter transit could help. If the crew reaches Mars in 56 days instead of about 259 days, they may arrive with less muscle loss, less bone loss, and better physical readiness. That matters for safety. It matters for productivity. It matters for emergencies. A crew that can move, think, repair, and respond quickly is a safer crew. But again, the shortcut does not remove the problem. It changes the mission tempo. A 35-day surface stay is short. The crew lands, recovers, checks the vehicle, begins surface work, handles science and engineering tasks, prepares for departure, and stays aligned with the return timeline. That is a very tight mission. There is less time to adapt, less time to rest, less time to delay operations after a hard landing, less time to repair equipment before the return window becomes critical. So the crew may arrive healthier, but they may have to work faster. That is not automatically safer. A long mission creates long-duration health risk. A short mission creates schedule pressure. A rapid Mars mission may reduce slow damage to the body, but increase the need for fast decisions and flawless operations. The human body is not the only system under stress. The crew's workload, sleep schedule, medical planning, and emergency response all become part of the risk equation. Psychology changes too. A traditional Mars mission can involve a very long time away from Earth. Months outbound, a long surface stay. Months back. That is a major isolation challenge. The crew lives in a closed environment with limited privacy, delayed communication, constant operational pressure, and no quick return. A 153-day or 226-day total mission changes that picture. Those numbers are still serious. They are not short in normal human terms, but compared with traditional Mars architectures that can last years, a sub-year round trip is a completely different psychological load. The crew knows the mission is intense but finite on a shorter scale. That could reduce some isolation stress. It could reduce the amount of food, water, oxygen, clothing, medical supplies, spare parts, and maintenance capacity required. Logistics would change too. A shorter total mission can reduce consumables mass. It can reduce how long life support must operate without resupply. It can reduce the amount of waste management needed. It can reduce the number of replacement parts required for the crew habitat. It can reduce some long-term reliability demands. But it can also remove flexibility. A long mission carries more supplies because it needs endurance. A short mission may carry less, but then every delay becomes more serious. If a surface system fails, there may not be months to work around it. If a crew member has a medical issue, the timeline may not allow slow recovery. If the return vehicle needs maintenance, the crew may have only weeks. If a dust storm affects operations, the schedule tightens immediately. Short missions reduce duration risk. They increase deadline risk. That is why the human question is not simply, is faster better? The real question is, does the total mission become safer? A rapid transfer may reduce radiation exposure, microgravity damage, isolation time, and consumables mass. Those are major benefits. But it may also increase departure energy, arrival violence, braking risk, surface schedule pressure, abort difficulty, and mission tempo. Those are major costs. A serious crewed mission analysis would have to compare both sides. It would need radiation dose estimates for the exact dates. It would need shielding mass and storm shelter design. It would need solar activity assumptions. It would need microgravity countermeasure plans. It would need artificial gravity studies if that option is included. It would need medical contingency planning. It would need life support reliability. It would need crew workload models. It would need abort mode analysis. It would need Mars entry loads, heating, and possible G-forces. It would need return re-entry planning. Only then can anyone say whether the shortcut improves safety. Because speed by itself is not safety. Speed is a trade. For example, cutting the outbound trip to 56 days could reduce the crew's radiation exposure before Mars arrival. But if the same route forces a dangerous high-speed aerocapture, the crew may face a severe acute risk in one event. The mission may exchange a slow risk spread over months for a concentrated risk during arrival. That may be worth it, or it may not. It depends on the numbers. This is why the 56-day route is more interesting than the 33-day route for human health. The 33-day trip reduces exposure even more, but it may create much more severe propulsion and braking problems. The 56-day trip still cuts the crews dramatically, while possibly giving engineers more room to manage arrival speed and mission systems. That does not make it easy. It makes it a more serious candidate for analysis. The 226-day total profile is especially important because it changes the idea of a Mars mission from a multi-year expedition into a shorter, high-intensity campaign. That could change astronaut selection. It could change training. It could change surface task planning. It could change how much equipment must be pre-positioned. It could change how much risk is acceptable for science versus exploration versus technology demonstration. But a short Mars mission also gives less time to recover from mistakes. That is the part that should stay uncomfortable. If the spacecraft arrives fast, the crew has less time before Mars operations. If the surface stay is short, the crew has less time to complete objectives. If the return window is tight, the crew has less time to solve problems before departure. If the mission returns fast, Earth re-entry may also be more demanding. So the shortcut may protect humans from the slow dangers of space, while pushing them into sharper mission events. That is the central human trade. Less radiation time, less microgravity time, less isolation time, but more pressure on propulsion, arrival, operations, and abort planning. This is why the CA-21 result is not just about reaching Mars sooner. It is about whether a different mission rhythm could be safer overall. Maybe the best crewed Mars architecture is not the slowest and most fuel-efficient one. Maybe it is not the fastest possible one either. Maybe it is a balanced route that cuts exposure time without making the arrival impossible. That is where the 56-day profile becomes serious. It suggests a possible middle ground between a long conventional cruise and an extreme 33-day sprint. It still needs advanced systems, it still needs a complete mission architecture, it still needs robotic testing. But it gives mission planners a concrete question to study. Can we spend more energy to reduce the time humans spend in deep space without creating a bigger danger at Mars? That is the question that matters. Not, can we fly faster? Can the total system become safer? And before anyone puts a crew on a route like this, the first passengers should not be humans. They should be instruments, sensors, heat shields, guidance systems, and robotic spacecraft sent to prove the shortcut does not hide a fatal flaw. No crew should be the first test of a route this aggressive. That is the rule. If a Mars shortcut demands high departure speed, precise timing, and dangerous arrival conditions, the first mission should not carry humans. It should carry instruments. It should carry sensors. It should carry systems designed to fail safely, because the first job is not exploration. The first job is proof. A trajectory can look strong in calculations, but space does not care about confidence on paper. Real spacecraft deal with navigation errors, thermal limits, communication delays, engine performance, solar activity, and small uncertainties that grow over time. A robotic test mission turns the idea from a calculation into measured data. That is how a speculative route becomes operational knowledge. The first test does not need to land. It does not even need to enter orbit. The simplest version would be a fast Mars flyby using a CA-21-like transfer plane. The spacecraft would launch onto the rapid geometry, perform cruise corrections, approach Mars, collect data, and fly past. That sounds less exciting than landing. But for a first test, it may be exactly right. A flyby avoids the hardest part, braking. It does not need Mars orbit insertion. It does not need aerocapture. It does not need parachutes. It does not need a landing system. It only needs to prove that the spacecraft can leave Earth on the right path, stay on the right path, and arrive at the correct place near Mars at the correct time. That is already a serious test, because this shortcut depends on precision. The timing must be right. The plane must be right. The arrival geometry must be right. The spacecraft must know where it is and where Mars will be. If it arrives too far off, the route is not useful. If corrections grow too large, the route may require more propellant than expected. If communication geometry becomes awkward, mission operations get harder. A small robotic flyby could measure all of that. It could carry cameras to confirm Mars approach geometry. It could carry radiation dosimeters to measure the real deep space radiation environment on a rapid path. It could carry plasma instruments to study the solar wind conditions during the cruise. It could carry optical navigation experiments to test whether the spacecraft can autonomously track stars, Mars, and other reference points during the approach. That last part matters a lot. On a fast route, there is less time to correct mistakes. Autonomous navigation becomes more valuable because waiting for ground commands can be slow. Mars may be minutes away in communication time, and decisions still have to be made carefully. The spacecraft needs to know its own position and correct small errors before they become large errors. A flyby would also test cruise correction behavior. In a normal long transfer, mission teams have more time to perform course corrections and refine the arrival. On a 56-day or 33-day trajectory, the correction timeline is compressed. Small errors may need to be identified earlier. Burn accuracy may matter more. Tracking quality may matter more. Navigation margins may shrink. So the first robotic mission would answer a basic question. Can a spacecraft actually fly this geometry cleanly? If the answer is no, humans should not go near it. If the answer is yes, the next step becomes harder. The next step would be testing Mars arrival. That could mean an aerocapture demonstrator or a high-speed atmospheric entry demonstrator. This is where the shortcut faces its most dangerous physical test. The spacecraft would not just fly past Mars, it would deliberately hit the atmosphere at high speed and measure what happens. That sounds extreme because it is, but it may be necessary. A rapid transfer is only useful for orbiting or landing if the spacecraft can slow down. Engines can do some of that, but carrying all the propellant for high-speed capture may make the mission too heavy. That is why aerocapture keeps appearing in this story. Mars' atmosphere could remove a large amount of speed without requiring the spacecraft to carry all that braking propellant. But aerocapture has to be proven. A demonstrator could enter the Martian atmosphere on a controlled path, test its heat shield, measure heating rates, measure G-loads, track atmospheric density, and prove that guidance can keep the spacecraft inside the safe corridor. It could try to exit into a planned orbit or simply test a high-speed entry profile with instruments. This would be a major step because high-speed atmospheric braking is not just one problem, it is many problems happening at once. The heat shield must survive. The structure must handle stress. The guidance system must respond quickly. The spacecraft must understand the atmosphere it is flying through. The navigation system must deliver the vehicle to the correct entry angle. The mission team must know whether the models were right. A crewed vehicle cannot be the first proof of that. Robots must take that risk first, and the testing should not stop with one spacecraft. A serious campaign could use multiple robotic missions. One fast flyby to test navigation and timing, one atmospheric demonstrator to test entry and heating, one aerocapture mission to test orbit capture, one cargo mission to test useful payload delivery. Each step reduces uncertainty before humans ever use the route. That is how high-risk exploration becomes controlled engineering. Cargo is another major test class. A cargo mission does not have the same constraints as a crewed mission. It can accept more risk, depending on the payload. It can travel slower when needed. It can be sent ahead years before the crew. It can prove parts of the architecture without risking lives. This is where the shortcut could become part of a split mission design. Cargo could go slow and efficient, crew could go fast and protected. That may be much more realistic than sending everything on the same high-speed path. Heavy cargo does not need a 56-day transfer. Habitats, supplies, power systems, spare parts, rovers, radiation shelters, and propellant tanks can take longer routes if that saves energy. The crew vehicle is the part where speed matters most because humans are vulnerable to radiation, microgravity, and life support duration. So instead of using the shortcut for everything, mission planners could use it for what benefits most from speed. Send the heavy things first, send the people later. That changes the risk equation. If a habitat is already waiting in Mars orbit or on the surface, the crew does not have to bring everything with them. If propellant is already staged, the return mission becomes less demanding. If a radiation shelter is already in place, the surface stay becomes safer. If a return vehicle is already checked out, the crew has a more reliable way home. The shortcut becomes more useful when it is part of a larger architecture. Not a single heroic flight. A prepared campaign. But even cargo missions need navigation proof. The CA-21 derived concept depends on precise timing and plane alignment, so navigation cannot be treated as a small detail. A test mission would need to validate the actual error growth along the route. It would need to measure how small launch errors change the arrival. It would need to test optical navigation. It would need to test autonomous correction planning. It would need to compare predicted ephemeris data with real spacecraft tracking. That is important because the study relies on real planetary positions and Lambert-style trajectory solutions. Those tools can identify a path, but a spacecraft must fly it with imperfect systems. Engines do not burn with perfect accuracy. Tracking is not perfect. Solar radiation pressure can slightly alter the path. Small forces can matter over long distances. Even with excellent models, mission designers need margins. Robots map those margins. Before humans fly the shortcut, robots must map its error bars. That is the most honest way to say it. The goal of early missions would not be to prove the route is exciting. That part is already clear. The goal would be to prove how wrong the models can be before the mission becomes unsafe. How much navigation error can the route tolerate? How much correction propellant is needed? How accurate must the launch be? How sensitive is Mars arrival? How much does the atmosphere vary during aerocapture? How much heat does the shield actually see? Those are the questions that decide whether the shortcut survives contact with reality. And robotic missions can answer them without risking a crew. The first spacecraft could be small, the second could be heavier, the third could test aerocapture, the fourth could deliver useful cargo. Each one would turn uncertainty into data. Each one would tell engineers whether the next step is justified. That is how this route would move from headline to hardware, not by announcing a crude 33-day Mars mission, not by assuming the 56-day profile is ready, by testing the pieces one by one: launch targeting, cruise navigation, correction burns, radiation environment, communication delays, Mars arrival velocity, atmospheric heating, G-loads, aerocapture control, orbit insertion, cargo delivery, return timing. Every part has to be proven, and the most important tests may not produce dramatic images. A navigation experiment is not as exciting as a human footprint. A heat shield sensor is not as emotional as a crew landing. But those quiet measurements are what decide whether humans can survive later. That is the serious path forward. The CA21-derived shortcut is not something you trust because it sounds revolutionary. You test it because it might be revolutionary. You send instruments first, you measure the route, you find the weak points, you improve the models, you test the braking, you stage cargo. Then only if the numbers close, you start talking seriously about humans. This is where the story becomes less like a discovery and more like a program. The math found a possible opening. Robots would have to prove it is usable, and even then, there is still one danger left that must be faced directly. The headline can make this sound like the future is already decided, but the science is more careful than that. The shortcut may be real as a trajectory opportunity, but it is not yet a full mission. And that distinction is where responsible skepticism begins. The most dangerous part of this story is not the asteroid. It is the headline. Scientists discovered a shortcut to Mars. Sounds like a finished breakthrough. It sounds like someone found a route. Engineers can build the ship and astronauts can launch. But that is not what the scientific claim actually says. The claim is narrower. A trajectory design method used early asteroid orbital data from 2001 CA21 and identified rapid Earth-Mars-Earth transfer opportunities for 2031. That is a serious result. It is worth paying attention to, but it is not the same as a mission approval. It is not the same as NASA selecting the route. It is not the same as a spacecraft being ready. That distinction matters because spaceflight does not forgive exaggeration. A trajectory opportunity is one layer of a mission. It says the math can connect departure, arrival, and return under certain assumptions. A mission design has to do much more. It has to close the propulsion budget. It has to carry real mass. It has to survive thermal loads. It has to handle navigation errors. It has to protect humans. It has to brake at Mars. It has to return to Earth safely. So the right way to say this is simple. The shortcut was identified in trajectory analysis. It has not been proven as a complete human Mars mission. That makes the story more credible, not less, because the real value is not that someone magically solved Mars travel. The real value is that asteroid data may reveal transfer opportunities that were not obvious through standard planning. But there is another caveat. The accessible preprint version is marked not peer-reviewed. That does not mean it is worthless. Preprints are often used to share research early. They can contain serious math, serious analysis, and useful ideas. But not peer-reviewed means the work has not gone through the full formal review process in that version. Other experts have not fully tested every assumption, checked every method, and challenged every conclusion through that channel. That means the language has to stay careful. The math is provocative, but full mission engineering is still unresolved. And even with a later journal listing connected to the work, the mission-level question remains. A published trajectory concept still needs independent reproduction. Other researchers need to test the same windows, the same assumptions, the same energy demands, and the same arrival conditions. They need to ask whether the results hold when spacecraft mass, real propulsion, navigation margins, thermal protection, and crew safety are included. That is normal science. A result becomes stronger when it survives challenge. And this result needs challenge because the numbers are extreme. The 33-day case is the obvious example. It is dramatic. It is the number people remember. Earth to Mars in 33 days sounds like the future arriving early. But the same reason it sounds impressive is the reason it is so difficult. A spacecraft that reaches Mars that fast must travel on a very high-energy path. It must leave Earth fast. It must arrive at Mars fast. It must then remove that speed without destroying itself. That is not a small engineering issue. That may be the central issue. The paper's own framing points toward high-energy missions, aerocapture, and advanced propulsion ideas like nuclear thermal propulsion. That tells you the author is not treating this as a simple near-term cruise. The route belongs to a high-energy mission class. It is not something you attach to a standard spacecraft and fly casually. So skepticism is not being negative. Skepticism is part of understanding the result. A fast transfer can be mathematically valid and still be beyond current practical capability. That is not a contradiction. It happens often in mission design. The equations may show that a path exists, but the vehicle needed to use that path may be too heavy, too hot, too expensive, too risky, or too far beyond available propulsion. That is why geometrically possible is not the same as operationally possible. Geometry can show the door. Engineering has to build the key. The propulsion caveat is huge. If the spacecraft needs more departure energy than current systems can provide for a useful payload, the route cannot fly as a crewed mission. If it needs orbital refueling, that refueling architecture has to exist. If it needs nuclear thermal propulsion, that system has to be developed, tested, certified, and integrated. If it needs staging, those stages have to be launched, assembled, and operated safely. Every solution adds complexity, and complexity adds failure modes. Then comes the landing caveat. Even if the spacecraft reaches Mars quickly, that does not mean it can do anything useful there. It has to brake. It has to enter orbit or land. If humans are aboard, it has to protect them through the most dangerous phase of the mission. A high-speed Mars arrival may require advanced aerocapture or a large propulsion burn. Either way, the mission becomes heavier and riskier. A spacecraft flying past Mars in 33 days is not a Mars mission. A spacecraft that can slow down safely is a Mars mission. That is the difference. And after Mars arrival, the mission still is not finished. If there is a surface stay, the crew has to survive landing, operate on the surface, and prepare to leave. If there is a return leg, the spacecraft has to depart Mars at the correct time. It has to follow another interplanetary path. It has to protect the crew again. Then it has to enter Earth's atmosphere safely. A shortcut that only solves the outbound leg is not enough. The CA21 study is more interesting because it includes round-trip profiles, but that still does not solve the full architecture. A round-trip trajectory is stronger than a one-way claim, but the hardware still has to make the round-trip possible. That includes Mars ascent or departure, Earth return speed, re-entry heating, crew recovery, communication coverage, and emergency options. Every high-speed advantage creates a matching high-speed problem. That is why the honest version of this story is better than the hype version. The hype version says, "We found a shortcut, Mars is now close, 33 days is possible, everything changes." The honest version says, "Asteroid-derived trajectory mining may reveal rare Mars transfer opportunities, including specific rapid 2031 profiles, but propulsion, braking, thermal protection, and mission safety still decide whether any of it can fly." The honest version is actually more interesting, because it points to a new method, not just a single claim. The real breakthrough may be the search strategy. Near-Earth asteroid catalogues are already full of orbital data. Those data were collected largely for planetary defense, but if early asteroid orbits can be used as candidate transfer planes, then the database becomes more than a hazard list. It becomes a source of trajectory clues. That is a serious idea. It means mission designers might search thousands of asteroid solutions for useful Earth-Mars, Earth-Venus, Earth-Asteroid, or Mars-return geometries. Most candidates will fail. Some may be too expensive. Some may work only for small robotic spacecraft. Some may reveal rare windows that deserve deeper analysis. This expands the design space. That is valuable even if the 33-day case never flies. A research result can matter because it changes how we search, not because it immediately becomes hardware. The next step is not to announce a crewed mission. The next step is independent reproduction. Other teams need to run the numbers. They need to test whether the 2031 alignment still looks strong under different assumptions. They need to compare the CA21-derived route with other rapid transfer options. They need to calculate mission-level delta V with realistic mass. They need to include launch vehicle limits. They need to model Mars arrival heating. They need to examine aerocapture feasibility. They need to test abort modes. And then robots need to fly. That is how this becomes real. First, reproduce the trajectory, then analyze the energy, then match it to possible propulsion, then test thermal protection, then fly a robotic demonstrator, then maybe start discussing human use. That order matters, because the worst version of this story would be to pretend the shortcut is already solved. That would weaken the science, it would make the results sound like another overhyped space headline, and it would hide the genuinely important part. The method may reveal transfer opportunities that old planning habits do not emphasize. So the skeptical conclusion is not, this is fake. The skeptical conclusion is, this is not finished. That is a much sharper point. There is a real difference between dismissing a result and understanding its limits. The CA21 route deserves attention because it connects asteroid data, orbital plane geometry, Lambert-style trajectory search, and a specific 2031 Mars alignment. That is meaningful, but it also deserves caution because fast transfers are energy hungry, arrival is brutal, and no full crewed mission architecture has been proven. Both things can be true. The concept can be exciting, the engineering can be unresolved, the shortcut can be real as a trajectory opportunity, the mission can still be far from ready, and that is exactly where the story should stand before the final synthesis. Not in hype, not in dismissal, in tension, because if the method holds up, it changes how we search for Mars routes. If the engineering improves, it could become part of a future mission architecture. If robotic tests confirm the navigation and arrival models, the case becomes stronger. But if propulsion, braking, or mass requirements do not close, the route stays on paper. That is the line between discovery and flight. The asteroid may have revealed a possible opening, but rockets, heat shields, guidance systems, and mission safety still decide whether anyone can pass through it. The real breakthrough is not that Mars suddenly became easy. The real breakthrough is that we may have been searching for Mars routes too narrowly. Classic Mars planning starts with known launch windows. Earth and Mars line up in useful ways roughly every 25 to 26 months, and mission designers build trajectories around those windows. The basic tools are familiar. Hohmann-style transfers, launch timing, Mars capture, atmospheric braking, gravity assists, and return geometry. That approach is still valid. But the CA21-inspired method adds another layer. It says asteroid orbit data may contain hidden geometric alignments. Near-Earth asteroids are already tracked for planetary defense. Their paths are calculated carefully because scientists need to know whether any of them could come close to Earth. But those same paths can also be searched for mission design clues. That is the shift. The data was built to answer one urgent question: what could threaten Earth? Now it may help answer another question: what paths through the solar system are worth testing? This does not replace normal Mars planning, it expands it. Instead of only starting with the standard Earth-Mars window and a familiar transfer family, scientists can also mine asteroid databases for planes, tilts, crossings, and timings that might reveal rare opportunities. That is why 2001 CA21 matters. The asteroid itself is not the mission. Its early orbit estimate became a clue. That clue pointed to a candidate plane. That plane was tested against real Earth-Mars timing. And in the model, 2031 produced rapid transfer profiles that stand far outside normal Mars mission expectations. That does not mean a spacecraft is ready. It means the search found something worth deeper study. And that is exactly how future Mars travel may develop. Not as one perfect route, Not as one universal answer, not as one magic transfer that solves everything. The future may use many different route classes for different mission needs. Cargo could travel slowly on low-energy paths. Robotic probes could use ballistic capture when saving insertion fuel matters more than saving time. Crewed spacecraft could use faster, higher energy transfers when reducing radiation and microgravity exposure matters most. Some missions could use gravity assists, some could use aerocapture, some could use nuclear thermal propulsion, some could use orbital refueling, some could use asteroid-derived trajectory templates to identify special windows. That is the more realistic future. Mars travel may not become easy. It may become more flexible. And flexibility matters because every mission has a different priority. A habitat module does not need to arrive in 56 days. A propellant tank does not care about isolation or bone loss. A robot can take a slower path if that saves mass. But a crew does care. Humans are exposed to radiation, microgravity, medical risk, and life support limits. For humans, time has a cost. That is why rapid crew transfer matters. A 56-day outbound trip could change the health equation. It could reduce deep space exposure. It could reduce microgravity damage. It could reduce consumables. It could reduce the psychological strain of a long cruise. But it would also demand higher energy, harder braking, and tighter mission operations. So the real question is not whether fast is better. The real question is whether the total mission becomes safer. That is the standard the CA-21 route must meet. It must not only look impressive in a trajectory study, it must survive the full mission architecture: launch, departure energy, cruise navigation, Mars arrival, heat shielding, aerocapture or propulsion capture, surface operations, Mars departure, Earth return, re-entry, crew survival. Every part has to close. That is why the balance claim is important. The shortcut is not a guaranteed 33-day human Mars mission. It is not proof that astronauts are about to fly to Mars in 1 month. It is not a NASA mission plan. It is not a finished vehicle design. It is a real astrodynamics clue. A CA-21-derived geometry produced specific rapid Earth-Mars-Earth profiles for 2031 in the study record. The numbers are concrete. The extreme profile is 33 days outbound, 30 days on Mars, and 90 days back for a total of about 153 days. The more feasible profile is 56 days outbound, 35 days on Mars, and 135 days back for a total of about 226 days. Those numbers matter because they challenge the normal scale of Mars travel. A standard Hohmann-style Earth-to-Mars cruise is about 259 days one way. So even the 56-day outbound case is a major reduction. The 33-day case is far more extreme, but the numbers must be understood correctly. They are proposed trajectory architectures, not approved mission schedules. That distinction protects the science from hype, because the hard problems remain. A fast spacecraft has to leave Earth with more energy. It has to arrive at Mars with more speed. It has to slow down without using impossible amounts of fuel or destroying itself in the atmosphere. It has to keep humans alive if humans are on board. It has to come back. The route does not remove physics. It changes the trade. Time goes down. Energy goes up. Chronic health risk may go down. Acute mission event risk may go up. Propulsion becomes more important. Aerocapture becomes more important. Navigation becomes more important. Thermal protection becomes more important. Robotic testing becomes mandatory before humans should be considered. That is why the next steps are clear. First, independent teams need to reproduce the trajectory results. Then they need to test the delta V requirements with realistic spacecraft mass. Then they need to compare the route with other fast transfer concepts. Then they need to study Mars arrival heating, G-loads, and braking options. And then they need to match the route with actual launch systems or future propulsion options. Then robotic missions need to test the path. A small fast flyby could test navigation and timing. An atmospheric demonstrator could test high-speed Mars entry. An aerocapture mission could test whether a spacecraft can safely turn arrival speed into orbit. Cargo missions could test useful delivery before any crew flies. That is the path from idea to hardware. Not hype, not dismissal, step-by-step proof. And the importance goes beyond Mars. If early asteroid orbit solutions can reveal a rapid Earth-Mars opportunity, similar methods could be tested for Venus missions, near-Earth asteroid missions, Mars sample return, cargo staging, and maybe even outer-planet mission planning.
The same principle applies. Use natural small-bodied trajectories to expose useful geometry in the solar system.
That does not mean every asteroid orbit becomes useful. Most will not. But with enough data, enough computation, and enough filtering, rare alignments can appear. A single useful plane, a single better timed return, a single lower penalty transfer, a single window that would not stand out in a basic search. That is why asteroid data matters. It turns planetary defense catalogues into a second kind of resource. Not only a warning system, but a search field for future mission routes. The same data that helps protect Earth could also help plan how to leave Earth more intelligently. That is the bigger change. For decades, Mars has been treated as far away not only because of distance, but because of timing, energy, and risk. This shortcut idea does not erase those barriers. It shows that some barriers may be negotiable under rare geometry. It shows that there may be more route families than the ones most people know. It shows that a future Mars campaign may combine slow cargo, fast crew, aerocapture, refueling, nuclear propulsion, ballistic capture, and asteroid-derived windows. No single method solves Mars, but together they change the design space, and that is how real progress usually starts. Not with a miracle route, with a better way to search, a sharper question, and a result strong enough to deserve testing. So the final claim should be direct. The 2001 CA-21 shortcut is not a finished road to Mars. It is not a promise of a 33-day crewed mission. It is not a reason to ignore propulsion, braking, radiation, or landing. It is a serious clue that asteroid data may reveal rapid transfer opportunities that standard planning can miss. The asteroid did not give us a road to Mars. It gave us a way to look for roads. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.